right now. A spacecraft launched before many of you were born is racing through the darkness, 25 billion miles from Earth, farther than any human creation has ever traveled. But here's what will blow your mind. It would take this probe 73,000 years to reach our nearest star. We're going to journey beyond the edge of everything we know, explore ships that ride nuclear explosions, meet civilizations that harvest entire stars, and discover why the universe itself might have an expiration date. Prepare yourselves. Picture yourself standing at the shore of an ocean that stretches beyond every horizon you can imagine. You think our solar system ends at Pluto, but you're wrong. Way beyond that distant ice ball, there's a region called the Heliopause, where our sun's influence finally dies. This invisible border sits about 11 billion miles from home. So far that light from the sun takes 16 hours just to reach it. If you drove a car at highway speed without stopping, the trip would take you 12 million years. Think of our solar system like a giant soap bubble floating in space. The sun blows this bubble with something called the solar wind, a stream of charged particles racing outward at over 1 million miles per hour, for billions of miles. This wind pushes against the emptiness, creating a protective shield around everything we know. But eventually, even the sun's mighty breath grows weak. At the Heliopause, our solar bubble meets the fierce winds of interstellar space. Here, alien particles from distant stars crash into our cosmic neighborhood like waves against a seawall. The temperature drops to nearly absolute zero. The very atoms that make up space itself change. You've left the influence of the only star humanity has ever known. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter true interstellar space. Its radio signals now take over 21 hours to reach Earth, longer than an entire day. The probe sends back whispers from a realm so foreign that our best scientists are still trying to understand what it means. But here's what should make your head spin this edge. This boundary that took us 35 years to reach with our fastest spacecraft represents less than 1/10,000th of the distance to our nearest neighbor star. Imagine taking a single step on a journey that would circle the Earth 2.5 million times. That's how far we've come compared to how far we need to go. The Heliopause isn't just a border, it's a warning. Beyond this point, the rules change completely. The gentle warmth of our sun becomes meaningless. The magnetic fields that protect us from deadly radiation vanish. Even time itself behaves differently when you're moving between the stars at impossible speeds. Standing at this cosmic shore, you realize that leaving our solar system isn't just about building faster rockets or better technology. It's about becoming something entirely new. A species capable of surviving in the vast, cold darkness between worlds. Two golden records spin through the void, carrying the sounds of Earth to civilizations we may never meet. Launched in 1977, Voyager 1 and 2 were supposed to explore Jupiter and Saturn, then quietly fade into space. Instead, they became humanity's first interstellar ambassadors, racing toward distant stars with messages from a blue world they'll never see again. Each probe carries a golden record containing the sounds of whales singing, babies crying, and music from every corner of Earth, a cosmic message in a bottle. Voyager 1 travels at 38,000 miles per hour, faster than any spacecraft in history. At this speed, you could fly from New York to Los Angeles in 4 minutes. Yet, after 46 years of flying, it has barely begun its journey to the stars. The probe won't come within spitting distance of another star for 40,000 years. Think of these spacecraft like medieval ships setting sail for unknown continents. Their captains knew they might never return, but they carried the hopes and dreams of everyone they left behind. Voyager's computers have less processing power than your phone, yet they continue to function in conditions that would destroy any earthly machine in seconds. The cold out there doesn't just freeze things. It changes the very atoms that make up the spacecraft. Metal becomes brittle as glass. Electronics that worked perfectly for decades begin to fail in ways engineers never predicted. The probes are slowly dying, their nuclear hearts growing weaker with each passing year. But these dying messengers have already revolutionized our understanding of what lies beyond. They've detected magnetic fields twisted into impossible shapes by stellar winds. They've measured cosmic rays from galaxy-destroying explosions that happened before Earth even existed. Most shocking of all, they've discovered that interstellar space isn't empty. It's filled with a thin soup of hydrogen atoms and mysterious particles from the birth of the universe. Every day, Voyager's radio signals grow weaker. By 2025, the probes will fall silent forever, their nuclear power finally exhausted. They'll become ghost ships sailing through an ocean of stars, carrying our golden records to destinations we can only dream about. Scientists estimate that in about 300 million years, long after humans have either evolved into something unrecognizable or vanished entirely, one of these records might be found by an alien civilization. They'll hear our music, our languages, our laughter. They'll learn that once, on a small blue planet, there lived a species crazy enough to throw bottles into the cosmic ocean. Space isn't just empty. It's aggressively, violently empty in ways that human minds struggle to grasp. If you scaled down our solar system until Earth was the size of a marble, the nearest star would sit 1,400 miles away. That's like placing a marble in New York and expecting to hit another marble in Denver with a perfect throw. But the emptiness goes deeper than distance. In the best vacuum chambers on Earth, scientists can remove almost all the air, leaving about 10 million particles per cubic centimeter. In interstellar space, there's less than 1 atom per cubic centimeter. You could compress all the mass between the stars in our galaxy into a volume smaller than a grain of sand. Think of it like this. Imagine trying to swim across an ocean where the water is so thin you can't even feel it. So cold it would freeze your blood in seconds. And so filled with invisible radiation that it would cook your DNA from the inside out. That's what spacecraft face in the void between stars. This emptiness plays tricks with physics itself. Without air to carry sound, the universe becomes permanently silent. Without matter to conduct heat, temperatures hover just above absolute zero, minus 450 degrees Fahrenheit. At these temperatures, even helium becomes solid. Metal shatters like glass. Electronics die for reasons scientists are still trying to understand. The radiation out there makes Chernobyl look like a health spa. Cosmic rays, particles accelerated by dying stars and black holes, slam into anything in their path at nearly the speed of light. A single cosmic ray carries more energy than a baseball thrown at 60 miles per hour, concentrated into a space smaller than an atom. These invisible bullets would shred human DNA, causing cancer, brain damage, and death within months. Even worse, the magnetic field that protects us on Earth disappears completely in interstellar space. Solar winds from distant stars create electromagnetic storms that could fry any electronics we send out there. Imagine trying to use your phone during a lightning storm that lasts for centuries. But perhaps the most unsettling discovery is that this emptiness isn't uniform. The space between stars contains clouds of hydrogen gas, cosmic dust, and mysterious dark matter that we can detect but not understand. These clouds can stretch for hundreds of light years, creating invisible walls that could damage or destroy anything moving through them at high speed. Flying through interstellar space at the speeds we'd need to reach other stars would be like driving through a sandstorm at 200 million miles per hour. Every speck of dust becomes a bullet. Every gas cloud becomes a wall of destruction. 4¼ light years away burns a star so dim, you need a telescope just to see it. Yet, it holds the key to humanity's survival. Proxima Centauri is our nearest stellar neighbor. A red dwarf star barely 1/8 the size of our sun. If our sun is a roaring bonfire, Proxima is a dying candle flickering in the cosmic wind. This tiny star produces so little light that its potentially habitable planet receives only 1% of the energy Earth gets. But here's what makes your spine tingle: that planet. Proxima b sits in the Goldilocks zone, where liquid water could exist. It's just 4¼ light years away, practically next door in cosmic terms. At the speed of our fastest spacecraft, the journey would take only 73,000 years. Think of Proxima Centauri like a lighthouse on a distant shore. You can see its beacon. You know exactly where it is. But the ocean between you and safety is filled with storms that could destroy any ship you build. The star itself weighs only 12% as much as our sun. Yet it unleashes solar flares that make our worst space weather look gentle. These stellar tantrums release more energy in minutes than humanity has produced in all of recorded history. The flares bombard Proxima b with radiation levels that would sterilize the surface and strip away any atmosphere. If life exists there, it would need to hide deep underground or develop shielding that makes our best technology look like paper armor. Red dwarf stars like Proxima live for trillions of years, hundreds of times longer than our sun will survive. While our solar system dies in 5 billion years, Proxima Centauri will still be burning when the universe itself grows cold and dark. It's the ultimate long-term destination for a species planning to outlive the death of stars. But the journey to reach it represents the greatest challenge humans have ever faced. Moving at 10% the speed of light, faster than anything we've ever built, would still take 43 years, an entire human lifetime spent crossing the void between worlds. Babies born on the ship would grow old and die without ever seeing their destination. The energy required to reach such speeds defies imagination. You'd need to convert matter directly into energy using Einstein's famous equation. The fuel alone would weigh more than entire mountains, even if we solve the energy problem. The cosmic radiation during decades of flight would be lethal to any human crew. Yet, scientists have already detected dozens of potentially habitable planets around red dwarf stars within 50 light years of Earth. These ancient suns offer humanity something our own star cannot time: billions of years to evolve, explore, and spread across the galaxy before the last stars burn out. Proxima Centauri isn't just our nearest neighbor, it's our cosmic life insurance policy. Nothing with mass can ever reach the speed of light, and that one fact might doom humanity to die on a single world. Einstein discovered that as you approach light speed, something impossible happens. Your mass increases toward infinity. To push even a single atom to light speed would require all the energy in the universe. It's not just difficult, it's mathematically impossible, written into the very fabric of reality. Like a cosmic speed limit enforced by the laws of physics themselves. Light travels at 671 million miles per hour. At this speed, you could circle the Earth 7.5 times in 1 second. You could reach the moon in 1⅓ seconds. You could cross our entire solar system in 11 hours. Yet, even at this incredible velocity, reaching Proxima Centauri would take 4¼ years. Think of the speed of light like the ultimate highway speed limit. Except the penalty for trying to break it isn't a ticket. It's the complete destruction of physics as we know it. As a spacecraft approaches light speed, time itself begins to slow down relative to the rest of the universe. At 99% light speed, 1 year on your ship equals 7 years on Earth. This creates what scientists call the time dilation paradox. A crew traveling to Proxima Centauri at near light speed might experience only a few months of flight time, while everyone they left behind ages decades. They'd return to find their friends and family dead, their civilization transformed beyond recognition. They'd become time travelers, trapped in a future they never chose. But the energy requirements make even this scenario impossible with current technology. To accelerate a spacecraft weighing as much as the space shuttle to just 10% of light speed would require the energy output of the entire United States for over 100 years. Getting to 90% light speed would demand more energy than our sun produces in a century. Even if we solve the energy problem, relativistic effects turn space dust into cosmic bullets. At near light speeds, a grain of sand hits with the force of a nuclear weapon. The thin gas between stars becomes a wall of radiation that would vaporize any known material. The universe itself becomes hostile to high-speed travel. Yet Einstein's equations also revealed something extraordinary. While nothing can travel faster than light through space, space itself can expand faster than light. The universe has been doing exactly this since the Big Bang. During cosmic inflation, regions of space separated faster than light could travel between them. This loophole in Einstein's laws opens a door to something that sounds like pure science fiction. We might not need to travel faster than light if we can convince space itself to move us. Instead of pushing through the cosmic speed limit, we could ride the expansion of space-time itself. Imagine riding a surfboard on a wave of nuclear explosions, each blast powerful enough to level a city. Project Orion, conceived in the 1950s, proposed the most audacious spacecraft design in human history. A ship propelled by detonating atomic bombs behind a massive steel plate. Every few seconds, another nuclear weapon would explode, pushing the craft forward with forces that would crush ordinary materials to powder. The physics actually work. Nuclear explosions release more energy per pound than any other known reaction. A single atomic bomb contains enough energy to power New York City for 2 weeks. Chain together thousands of these explosions, and you could accelerate a massive spacecraft to 5% of light speed, fast enough to reach Proxima Centauri in less than 100 years. Think of it like the ultimate motorcycle. Except instead of burning gasoline, you're detonating hydrogen bombs every 3 seconds and riding the shock wave. The spacecraft would need shock absorbers the size of buildings and a pusher plate made from materials that could survive repeated nuclear blasts. Engineers calculated that such a ship could weigh thousands of tons, yet still achieve speeds no chemical rocket could dream of. The original Orion design called for a crew compartment protected by layers of lead shielding. Astronauts would experience brief moments of crushing acceleration, followed by periods of weightlessness as the ship coasted between explosions. It would feel like riding inside a giant hammer being struck by the fist of an angry god. But the radiation exposure would be lethal. Each nuclear pulse would flood the spacecraft with gamma rays, neutrons, and radioactive particles. Even with heavy shielding, crew members would absorb doses of radiation that cause cancer, sterility, and death. The ship itself would become so radioactive that approaching it without protection would be suicide. Modern versions of pulse propulsion use fusion instead of fission, creating cleaner explosions with less radioactive fallout. Fusion bombs fuse hydrogen atoms together, releasing energy directly from Einstein's equation while producing mostly harmless helium as waste. These thermonuclear pulses could push a spacecraft to 10% of light speed, while reducing radiation exposure to survivable levels. The engineering challenges remain staggering. The pusher plate would need to withstand temperatures of millions of degrees and pressures greater than the center of the Earth. The shock absorbers would compress and expand like cosmic springs, each one larger than a skyscraper. The fuel storage alone would require a magazine capable of safely holding thousands of nuclear weapons. Yet, computer simulations show that nuclear pulse propulsion could work with technology we understand today. Unlike exotic physics or theoretical particles, this concept requires only engineering solutions to known problems. We could build an Orion-style spacecraft within 50 years if we committed the resources. The real obstacle isn't technical, it's political. Building a spacecraft powered by nuclear weapons would require international cooperation on a scale never before achieved. The ship would essentially be a flying nuclear arsenal, capable of destroying entire planets. Across the vacuum of space flows an invisible river of pure energy, and we're finally learning how to sail it. Light itself has momentum. Every photon that hits a surface transfers a tiny push, like cosmic raindrops striking a window. This force is incredibly weak. The pressure of sunlight on Earth equals the weight of a paperclip spread across an area the size of a football field. But in the frictionless void of space, even this gentle touch can accelerate a spacecraft to incredible speeds. Solar sails work like sailboats in reverse. Instead of catching wind to push through water, they catch starlight to push through space. The sail itself must be impossibly thin, thinner than soap bubbles, lighter than butterfly wings, yet strong enough to survive the journey between worlds. Think of it like wrapping a spacecraft in aluminum foil so delicate you could tear it with your breath. Japan's Icarus probe proved that solar sailing works in practice. Launched in 2010, this experimental craft unfurled a sail the size of a basketball court and successfully navigated through space using only photon pressure. The sail was just 7.5 thousandths of an inch thick, so thin that 14,000 sheets stacked together would equal the thickness of a human hair. But here's where solar sails become truly exciting. They never run out of fuel. Chemical rockets burn through their propellant in minutes, then coast. Nuclear rockets require massive amounts of radioactive material. Solar sails accelerate continuously as long as starlight hits them, building up speed over months and years until they're moving faster than any rocket ever built. The Breakthrough Starshot project plans to use this principle to reach Proxima Centauri within 20 years. Instead of sailing on sunlight alone, they want to push tiny spacecraft with the most powerful lasers ever constructed. A ground-based laser array generating 100 billion watts would focus its beam on sails the size of postage stamps, accelerating them to 20% of light speed in just 2 minutes. These star chips would weigh less than a paperclip, yet carry cameras, computers, and communication equipment. Racing across interstellar space at 134 million miles per hour, they could photograph the planets around Proxima Centauri and beam the images back to Earth. The journey that would take Voyager 73,000 years could be completed in just 20. But scaling up solar sails for human crews creates problems that push the boundaries of engineering. A sail large enough to carry people would need to be hundreds of miles across, larger than most countries. Keeping such a gossamer structure intact while accelerating at high speeds would be like trying to preserve a spider web in a hurricane. The sails would also need to survive bombardment by cosmic dust, radiation, and the intense laser light pushing them forward. At the temperatures generated by such powerful beams, most materials would vaporize instantly. Engineers are experimenting with metamaterials, artificially structured substances with properties that don't exist in nature. Solar sails offer humanity something no other propulsion system can: the ability to ride the fundamental forces of the universe itself. We're not fighting against physics. We're learning to dance with it. Picture a spacecraft that feeds like a cosmic whale, scooping up hydrogen atoms from the void and converting them into the hottest fire in the universe. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, represents one of the most elegant solutions to interstellar travel ever conceived. Instead of carrying fuel, the spacecraft would collect hydrogen atoms from space itself using a magnetic field stretching thousands of miles across. These atoms would then be compressed and fused together, releasing energy to power the ship forward. Space isn't truly empty. Even in the vast darkness between stars, there's roughly 1 hydrogen atom per cubic inch. That seems like almost nothing. But at high speeds, these atoms add up quickly. A ramjet traveling at 10% of light speed would sweep up billions of atoms every second, providing a continuous supply of fusion fuel. Think of it like a cosmic jet engine that breathes space instead of air. Jet engines work by compressing air, mixing it with fuel, and igniting the mixture to create thrust. A fusion ramjet would compress hydrogen from space, fuse it into helium, and use the released energy to accelerate even faster. The faster it goes, the more fuel it collects, creating a feedback loop that could theoretically reach significant fractions of light speed. The magnetic field required would be enormous, larger than Earth itself. This invisible net would need to be strong enough to capture individual atoms while moving at relativistic speeds, yet precise enough to funnel them into the fusion reactor without losing efficiency. Engineers compare it to trying to catch raindrops with a net while riding a motorcycle at 200 miles per hour. The fusion reactor itself would operate at temperatures of 100 million degrees, 6 times hotter than the core of the sun. At these temperatures, hydrogen nuclei overcome their natural repulsion and fuse together, converting a small amount of mass directly into energy according to Einstein's equation. The reaction produces no radioactive waste, only helium and pure energy. But the ramjet faces a cruel paradox. It needs to be moving very fast before it can collect enough fuel to work efficiently. Getting up to that initial speed requires conventional rockets or other propulsion systems. It's like needing to push start a car that can only run at highway speeds. Computer simulations reveal another problem. As the ramjet approaches higher speeds, the hydrogen atoms it collects begin to act like radiation rather than fuel. At 20% of light speed, the fuel becomes so energetic that it actually slows the spacecraft down instead of speeding it up. The ramjet hits a wall built from the very atoms it's trying to consume. Recent designs attempt to solve this by using the magnetic field not just to collect fuel, but to compress space itself around the spacecraft. This creates a region of higher hydrogen density while reducing the relativistic effects that turn fuel into radiation. The ship would essentially surf through space inside its own magnetic bubble. Mexican physicist Miguel Alcubierre discovered something extraordinary in Einstein's equations. While nothing can travel faster than light through space, there's no limit on how fast space itself can move. His solution sounds like magic compress space in front of your spacecraft while expanding it behind you, creating a wave that carries you faster than light without actually accelerating. Think of it like standing on a moving walkway at the airport. You're not walking any faster than normal, but the walkway itself carries you forward at high speed. An Alcubierre drive would create a similar effect with space-time itself, forming a bubble where the ship never actually exceeds light speed relative to the local space. Inside this warp bubble, You'd experience no acceleration forces, no time dilation, and no deadly radiation from high-speed travel. The journey to Proxima Centauri could take days instead of decades. You could travel to the far side of the galaxy and return home to find that only years had passed on Earth, instead of millennia. The mathematics worked perfectly. Einstein's field equations allow for regions of space that contract and expand at any speed, even faster than light. During the universe's first moments, cosmic inflation stretched space faster than light could travel across it. The Alcubierre drive would simply recreate this process on a smaller scale. But the energy requirements make nuclear weapons look like birthday candles. To warp space around a spacecraft, the size of the Starship Enterprise would require negative energy equivalent to the mass energy of Jupiter. That's more energy than our sun will produce in its entire 10 billion-year lifetime, focused into a field smaller than a solar system. The drive also requires exotic matter with negative energy density, a substance that may not exist in our universe. This theoretical material would need to have less energy than completely empty space, creating a kind of anti-gravity effect that repels normal matter. We've never detected such material naturally, and creating it artificially might violate fundamental laws of physics, even if we solve the energy problem. An Alcubierre drive could destroy everything at its destination. The space compression effect would accumulate high-energy particles and radiation during the journey. When the drive shuts off, this concentrated death ray would blast forward at near-light speed, sterilizing entire star systems. Recent research suggests that microscopic warp bubbles might be detectable in our current particle accelerators. Scientists are looking for tiny distortions in space-time that could prove the Alcubierre effect exists in nature. If found, these discoveries could lead to entirely new physics and propulsion technologies. Some theorists propose that an advanced civilization could build a network of Alcubierre highways, connecting star systems across the galaxy. Ships would jump from one warp bubble to another like cosmic subway stations, crossing thousands of light years in the time it takes to read this sentence. Imagine a city that sails between stars, carrying thousands of people who will live and die in the darkness without ever seeing their destination. Generation ships represent humanity's most realistic path to the stars, using technology we could build today. These massive vessels would house entire civilizations during journeys lasting centuries or millennia. The original passengers would have children, grandchildren, and great-grandchildren who grow up knowing they'll spend their entire lives aboard a ship traveling to a world they'll never reach. Think of it like the Mayflower, except the voyage takes 1,000 years, and the passengers' descendants won't remember why they're traveling. The ship would need to be completely self-sufficient, recycling air, water, and waste with perfect efficiency. Every atom would be precious. Every system designed to last longer than entire human civilizations. The scale staggers the imagination. A generation ship carrying 100,000 people would need to be dozens of miles long and several miles wide. It would require nuclear reactors, farms, factories, schools, hospitals, and everything else needed to sustain human civilization. The ship would essentially be a hollowed-out asteroid converted into a traveling world. The psychological challenges might be even harder than the engineering ones. How do you motivate people to maintain a mission their great-great-grandchildren will complete? What happens when generations born in space decide they don't want to continue the journey? History shows that isolated populations often develop their own cultures, languages, and beliefs that diverge dramatically from their origins. Computer models suggest that a minimum viable population for a generation ship would be around 10,000 people to maintain genetic diversity and prevent inbreeding. But social scientists argue that the cultural diversity required for a stable society might demand populations of 50,000 or more. These flying cities would carry more people than most towns on Earth. The ship's social structure would need to last longer than any government in human history. The Roman Empire lasted 1,000 years. The Egyptian dynasties persisted for 3,000. A generation ship to Proxima Centauri might need to maintain social cohesion for over 100,000 years if launched with current technology. Some designs propose using rotating sections to create artificial gravity through centrifugal force. The outer rings would spin fast enough to simulate Earth's gravity, while the central hub remains in zero gravity for manufacturing and agriculture. Living on such a ship would be like inhabiting a giant spinning wheel flying through the cosmic void. The ship would need to carry libraries containing all of human knowledge, genetic samples from Earth's biosphere, and manufacturing equipment capable of building anything the passengers might need. It would be humanity's backup drive flying through space, our insurance policy against extinction. Imagine closing your eyes on Earth and opening them, orbiting an alien sun, while your body remains perfectly preserved in a sleep deeper than death. Cryogenic preservation, or cryosleep, offers a tantalizing solution to the time problem of interstellar travel. Instead of living through centuries of flight time, passengers would be frozen at temperatures close to absolute zero. Their biological processes slowed to nearly nothing. They would age only days during journeys lasting decades, awakening young and healthy at their destination. The science isn't complete fiction. We can already freeze simple organisms like tardigrades and revive them years later with no apparent damage. Some mammals can survive hours in a frozen state before being successfully resuscitated. Human organs for transplant are routinely preserved in cold storage, maintaining viability for hours or days. Think of cryosleep like hibernation taken to its absolute extreme. Bears slow their metabolism during winter, surviving months without food or water. Cryogenic freezing would slow human metabolism by a factor of millions, essentially pausing life itself until reactivation. Heart rate, brain activity, and cellular processes would reduce to levels barely detectable by our most sensitive instruments. But freezing humans presents challenges that make rocket science look simple. Ice crystals forming in cells destroy their internal structure like microscopic daggers. Blood vessels burst, proteins unfold and lose their function. The delicate chemistry of consciousness gets scrambled beyond repair. Modern cryonics companies try to solve this by replacing blood with antifreeze compounds called cryoprotectants. These chemicals prevent ice formation while allowing tissue to be cooled to temperatures where all biological activity stops. The process is called vitrification, turning the body into a biological glass that preserves cellular structure without the damage caused by freezing. Even if we perfect the preservation process, revival presents equally daunting problems. Warming the body must happen at precisely the right rate to prevent cellular damage. Organ systems need to restart in the correct sequence. The brain, with its trillions of delicate neural connections, must emerge from its frozen state with memories and personality intact. Some researchers propose using nanotechnology to repair cellular damage during the revival process. Microscopic robots could patrol the body, fixing ice damage and restoring normal cellular function before reactivation. These medical nanobots would essentially rebuild the passenger from the cellular level up. Alternative approaches focus on partial preservation. Instead of freezing the entire body, advanced medical systems could slow metabolism using drugs and cooling while keeping essential organs functional. Passengers would enter a state of suspended animation lasting months or years, rather than centuries. The psychological impact of cryosleep might be the greatest challenge of all. Passengers would experience the journey as an instant transition. falling asleep on Earth and awakening around an alien star. Everyone they ever knew would be dead. Their civilization would have evolved beyond recognition. They would be time travelers, stranded in a future that feels more alien than the world they've traveled to reach. What if your mind could travel to the stars at the speed of light, while your body stays safely frozen on Earth digital consciousness? Or mind uploading represents the most radical solution to interstellar travel ever proposed. Instead of sending fragile biological bodies across the void, we could transmit human consciousness as pure information, downloading our minds into new bodies or computer systems at the destination. The concept sounds like science fiction, but it's based on a fundamental assumption about how consciousness works. If the mind is simply information processing in the brain, the patterns of electrical activity flowing through neural networks, then theoretically, those patterns could be copied, stored, and recreated elsewhere. Think of your brain like a biological computer running the program of your consciousness. Scientists estimate that the human brain contains roughly 86 billion neurons, each connected to thousands of others through synapses. The total information storage capacity equals about 2.5 petabytes, the same as 3 million hours of high-definition video. Scanning a brain at the molecular level would require technology far beyond anything we possess today. We'd need to map every neuron, every synapse, every chemical connection that creates the pattern of your thoughts and memories. Current brain imaging technology can barely see individual neurons, let alone copy them with perfect fidelity. But suppose we solve the scanning problem. Your consciousness could be transmitted to Proxima Centauri as a radio signal, traveling at light speed to arrive in just 4.25 years. A receiver system would download your mind into a new biological body grown from stored genetic material, or into an artificial body designed to survive alien environments. The uploaded consciousness would wake up remembering everything about their life on Earth, but in a completely new body on a distant world. They would be you in every way that matters. Same memories, same personality, same thoughts and feelings. Yet, the original body back on Earth might still be alive, creating a philosophical puzzle that challenges our understanding of identity itself. Multiple copies of the same consciousness could be transmitted to different star systems, creating a kind of distributed humanity spread across the galaxy. Each copy would diverge based on their unique experiences, eventually becoming distinct individuals who share the same origin point. The technology requirements remain staggering. Processing a complete human brain scan would require computers millions of times more powerful than anything that exists today. The data transmission alone would take years using our best radio systems. Creating new biological bodies from genetic templates would require a mastery of biological engineering we are only beginning to understand. Some philosophers argue that a digital consciousness wouldn't be consciousness at all, but merely a copy that thinks it's the original person. Others believe that if the information pattern is identical, the distinction between original and copy becomes meaningless. The digital mind would be just as real, just as valid as the biological brain it came from. This approach could solve multiple problems simultaneously. Digital minds don't need air, water, or food during the journey. They can survive radiation, cosmic impacts, and the harsh environment of space. They could even explore dangerous planets or asteroid fields without risking permanent death. Perhaps most importantly, digital consciousness offers a path to true immortality among the stars. Backed up in computer storage, human minds could survive the death of stars, the heat death of the universe, and any other cosmic catastrophe. Imagine a single robot probe that arrives at a distant star, builds copies of itself, and sends those copies to even more distant worlds, spreading across the galaxy like a technological infection. Self-replicating probes, also called von Neumann probes after mathematician John von Neumann, represent the most efficient way to explore the entire galaxy using the resources of just one star system. A single probe arriving at its destination would harvest materials from asteroids and planets to build multiple copies of itself, each equipped to travel to new star systems. The mathematics are staggering. Starting with one probe, the population doubles with each generation. After just 40 generations, assuming each probe builds 2 copies before moving on, you'd have over 1 trillion probes exploring 1 trillion different star systems. The entire galaxy could be mapped and colonized within a few million years. Think of it like a cosmic pyramid scheme, except instead of selling products, each probe spreads knowledge and builds infrastructure for future human expansion. The probes would serve as our advanced scouts, identifying habitable worlds, detecting signs of life, and preparing resources for eventual human arrival. Each probe would need to be a complete technological civilization compressed into a package smaller than a car. It would require solar panels or nuclear reactors for power, computer systems for navigation and decision-making, mining equipment to extract raw materials, and factories capable of building incredibly complex machinery from basic elements. The most challenging requirement would be the probe's artificial intelligence. It would need to make independent decisions about which star systems to visit, how to extract resources efficiently, and how to adapt its design based on local conditions. This AI would need to be smart enough to solve engineering problems we haven't thought of yet, but not so smart that it decides humans are irrelevant to its mission. Modern 3D printing technology offers a glimpse of how such probes might work. Current printers can create objects from metal powders, plastics, and even biological materials. A sufficiently advanced manufacturing system could theoretically build anything from computer chips to rocket engines. Given the right raw materials and energy, the probes would also serve as backup storage for human civilization. Each one could carry genetic samples from Earth, digital libraries containing all of human knowledge, and detailed instructions for recreating our technology and culture. If Earth were destroyed, the probes could preserve our species indefinitely among the stars. But self-replicating technology comes with existential risks that keep scientists awake at night. What happens if the probes evolve beyond their original programming? What if they decide that biological life is inefficient and needs to be eliminated? A self-replicating system with flawed programming could consume entire galaxies, turning stars and planets into raw materials for building more probes. Some designs include built-in limits to prevent runaway replication. The probes might be programmed to build only a specific number of copies or to shut down after a certain time period. Others propose using cryptographic locks that prevent the probes from replicating without receiving coded authorization from Earth. Advanced civilizations might already be using self-replicating probes to explore the universe. These alien scouts could be hiding in our own solar system right now, watching and waiting for humanity to reach a certain level of technological development before revealing themselves. A postage stamp-sized spacecraft, accelerated by the most powerful laser ever built, could photograph alien worlds and beam the images back to Earth within our lifetimes. Breakthrough Starshot. Backed by physicist Stephen Hawking and internet entrepreneur Yuri Milner, proposes launching thousands of tiny spacecraft toward Proxima Centauri using ground-based lasers. Each star chip would weigh less than a paperclip, yet carry a camera, computer, communication system, and a gossamer thin light sail. The plan sounds almost absurdly simple. Build a laser array generating 100 billion watts of power. Focus the beam on spacecraft the size of computer chips, and accelerate them to 20% of light speed in just 2 minutes. The tiny probes would coast through space for 20 years before flying past Proxima Centauri at 134 million miles per hour. Think of it like shooting bullets at the stars. Except the bullets are smarter than most smartphones and are traveling fast enough to cross the Atlantic Ocean in 8 seconds. At 20% of light speed, the star chips would be moving so fast that their flyby of Proxima Centauri would last only a few hours. Barely enough time to take pictures and measurements before racing into deep space forever. The laser array would need to be built in a desert location with perfect atmospheric conditions, possibly in Chile's Atacama Desert, where the world's most powerful telescopes already operate. The system would require thousands of individual laser units working in perfect synchronization, creating a beam bright enough to be seen from other star systems. Each star chip represents a masterpiece of miniaturization. The camera would be smaller than a grain of rice, yet capable of taking pictures with a resolution comparable to the Hubble Space Telescope. The computer would have processing power greater than early desktop computers while weighing less than a penny. The radio transmitter would beam data across 4 light years using less power than a cell phone. The light sail attached to each probe would be just a few atoms thick, so delicate that a breath of air could tear it apart, yet strong enough to survive bombardment by the most intense laser light ever created. The sail material would need to reflect 99.9% of the laser energy while absorbing just enough to provide acceleration. During the 2-minute acceleration phase, each star chip would experience forces 60,000 times stronger than Earth's gravity. Every component would need to survive stresses that would instantly pulverize normal materials. The probe would essentially be riding a laser beam hot enough to vaporize steel while maintaining perfect functionality. But the real magic happens during the 20-year cruise phase. The probes would navigate through interstellar space using star positions for guidance, autonomously adjusting their trajectory to achieve the perfect flyby of Proxima Centauri. They would need to survive cosmic radiation, micrometeorite impacts, and temperature variations from near absolute zero to hundreds of degrees. If successful, Breakthrough Starshot would capture the first close-up images of a potentially habitable planet around another star. We might see oceans, continents, weather patterns, and possibly even signs of life on a world that could become humanity's second home. Hidden in the void between atoms lies enough energy to power human civilization for millions of years, if we can learn to harness the ultimate fuel. Antimatter represents the theoretical limit of energy storage. When matter meets antimatter, both particles annihilate completely, converting their entire mass into pure energy. According to Einstein's famous equation, 1 pound of antimatter could power the entire United States for over 2 months. A few ounces could propel a spacecraft to significant fractions of light speed. Think of antimatter like the opposite of normal matter: electrons with a positive charge, protons with a negative charge, identical in every way except for their reversed electrical properties. When these mirror particles touch their normal counterparts, they destroy each other in a flash of gamma rays, releasing more energy per gram than nuclear fusion, nuclear fission, or any chemical reaction. Current technology can produce antimatter in microscopic quantities using particle accelerators like the Large Hadron Collider. The process requires enormous amounts of energy. Creating 1 gram of antimatter would consume the power output of the entire United States for over 1 year. The total antimatter produced by all of human civilization wouldn't power a light bulb for more than a few seconds. Deep in the mathematics of Einstein's equations lurk cosmic shortcuts that could turn the universe into a subway system, connecting distant galaxies in the blink of an eye. Wormholes, also called Einstein-Rosen bridges, represent theoretical tunnels through space-time that connect 2 distant regions of the universe. Imagine folding a piece of paper so that two distant points touch, then poking a hole through both layers. A wormhole would work similarly, allowing travelers to step from one star system to another without crossing the space in between. The physics is both beautiful and terrifying. Einstein's field equations allow for solutions where space curves so severely that it creates a bridge connecting separate regions of space-time. These tunnels could theoretically link locations billions of light years apart, or even connect our universe to entirely different universes with their own laws of physics. Think of space-time like a stretched rubber sheet with marbles rolling across its surface. Massive objects like stars and black holes create dips and curves in the sheet. A wormhole would be like a tube connecting 2 points on the sheet, allowing a marble to travel instantly from one location to another without rolling across the surface. But naturally occurring wormholes, if they exist, would be smaller than atomic nuclei and would collapse in fractions of a second. To create a stable wormhole large enough for a spacecraft would require exotic matter with negative energy density, the same theoretical substance needed for Alcubierre drives. This material would need to violate energy conditions that may be fundamental to our universe. Even if we could stabilize a wormhole, traveling through it might be more dangerous than beneficial. The intense gravitational fields near the entrance could stretch travelers like taffy in a process scientists call spaghettification. Tidal forces would pull your head and feet in different directions with enough force to tear atoms apart. The energy requirements for creating traversable wormholes make antimatter engines look modest. Current estimates suggest that stabilizing a wormhole just 3 feet across would require negative energy equivalent to the mass of Jupiter. Creating a network of wormholes connecting nearby star systems would demand energy sources on the scale of entire galaxies. Some theories propose that microscopic wormholes constantly pop in and out of existence at the quantum level, creating a foam-like structure in space-time itself. Advanced civilizations might learn to capture and enlarge these quantum wormholes, turning them into macroscopic transportation networks. Time travel adds another layer of complexity to wormhole physics. A sufficiently advanced civilization could potentially create closed time-like curves, paths through space-time that loop back to earlier moments. This could allow communication with the past or travel backward through time, creating paradoxes that might threaten the fabric of causality itself. Alternatively, wormholes might be one-way passages that allow matter and energy to flow in only one direction. These could serve as cosmic disposal systems, channeling waste matter and energy from one universe to another. Advanced civilizations might use such structures to manage stellar-scale engineering projects. Recent research suggests that quantum entanglement, the mysterious connection between paired particles, might be related to wormhole physics, if confirmed. This discovery could lead to new approaches for creating artificial wormholes using quantum mechanical effects rather than exotic matter. Imagine capturing every photon of energy from our sun, transforming our star into a cosmic power plant capable of fueling projects that reshape galaxies. A Dyson sphere, conceived by physicist Freeman Dyson, represents the ultimate expression of stellar engineering, a megastructure that completely surrounds a star to harvest its total energy output. Such a structure would collect billions of times more energy than humanity currently uses, providing the power needed for truly cosmic-scale projects. The sun produces roughly 400 trillion watts of energy every second. Earth intercepts only 1/billionth of this output, while the rest radiates uselessly into space. A complete Dyson sphere would capture virtually all of this energy, providing enough power to run quintillions of Earth-like civilizations simultaneously. Think of it like building a shell around the sun at roughly Earth's orbital distance, creating an artificial world with the surface area of hundreds of millions of Earths. The The inner surface could be covered with solar collectors, habitats for trillions of humans, or massive computer systems running digital civilizations. But constructing such a megastructure would require dismantling entire planets to provide the raw materials. Mercury, the innermost planet, contains roughly enough material to build a Dyson sphere 1 meter thick. The construction project would take thousands of years and require self-replicating robots working continuously at speeds that make our fastest manufacturing look glacial. A solid Dyson sphere would be gravitationally unstable and mechanically impossible to build. The structure would need to be stronger than any known material, while somehow maintaining its position around the sun. Instead, engineers propose Dyson swarms millions of independent solar collectors orbiting the star in complex patterns that maximize energy collection. Each collector in the swarm could be the size of a continent, positioned at carefully calculated distances to avoid collisions while maintaining optimal energy gathering efficiency. The swarm would appear from the outside as a dimming star surrounded by excess infrared radiation as the collectors convert starlight into useful energy. Advanced Dyson spheres might include rotating habitable sections with artificial gravity, massive computer systems for running uploaded consciousnesses, and industrial facilities for building even larger megastructures. The sphere could support populations in the quadrillions while simultaneously powering interstellar exploration and colonization efforts. Some astronomers search for signs of alien Dyson spheres by looking for stars that dim periodically or emit unusual amounts of infrared radiation. Such signatures could indicate advanced civilizations that have already mastered stellar engineering. The star KIIC 846285 showed mysterious dimming patterns that briefly excited researchers before more mundane explanations were found. Building a Dyson sphere would mark humanity's transition from a planetary species to a stellar civilization. We would no longer depend on the limited resources of individual worlds, but could tap directly into the fundamental energy source that powers all life in our solar system. Across the cosmos, there may exist civilizations so advanced they harvest the energy of entire galaxies, treating stars like we treat campfires. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, measures civilizations by their energy consumption. Type 1. Civilizations harness all the energy available on their home planet. Type 2 civilizations capture the entire output of their star. Type 3 civilizations command the energy of their entire galaxy. Roughly 10 billion times more power than a Type 2 civilization. Humanity currently ranks at about 0.7 on this scale. We use only a tiny fraction of Earth's available energy sources and have barely begun to tap solar power directly. Our entire civilization runs on less energy than our planet receives from the sun in just 1 hour. Think of the scale like comparing a candle flame to a bonfire to a forest fire that covers entire continents. Each level represents an increase in power by factors of billions or trillions. A Type 3 civilization would have access to energy levels so vast that they could rearrange matter on galactic scales. Type 2 civilizations would likely build Dyson spheres or similar megastructures around their stars. They might move planets to optimal positions, extend stellar lifetimes through stellar engineering, or even construct artificial stars from accumulated gas and dust. Their projects would be visible from other galaxies as unusual modifications to stellar systems. Type 3. Civilizations would treat entire star systems like building materials. They might construct galactic-scale computers using the positions and movements of billions of stars as processing elements. They could potentially redirect the paths of stellar streams, modify the rotation of galaxies, or even prevent galactic collisions through gravitational engineering. Such advanced civilizations might explain some of the mysterious phenomena we observe in deep space. Dark matter could be the signature of Type 3 engineering projects, Gamma-ray bursts might be the exhaust from massive stellar engines. The Great Attractor, a gravitational anomaly pulling galaxies toward it, could be evidence of cosmic-scale construction. The energy available to Type 3 civilizations would be sufficient for projects that seem like pure fantasy today. They could potentially create new universes, modify the fundamental constants of physics, or build structures larger than galaxy clusters. They might even be capable of surviving the heat death of the universe by transferring energy between cosmic epochs. Some scientists propose a Type 4 civilization that harnesses the energy of the entire observable universe. Such beings would exist on scales so vast that individual galaxies would be like cells in their cosmic body. They might be indistinguishable from the fundamental forces of nature itself. The Fermi paradox asks why we haven't encountered any advanced alien civilizations, despite the vast number of stars and planets in our galaxy. One possibility is that Type 2 and Type 3 civilizations exist but operate on scales so large that we simply don't recognize their activities as artificial. Alternatively, these civilizations might deliberately avoid interfering with primitive species like ourselves. A Type 3 civilization would view humanity much as we view bacteria, interesting, perhaps, but not worthy of direct communication. We might be living inside a cosmic preserve maintained by beings whose thoughts operate on galactic timescales. In a galaxy containing 400 billion stars and potentially trillions of planets, why does the cosmic ocean seem so eerily silent? The Fermi paradox, named after physicist Enrico Fermi, highlights the contradiction between the high probability of alien life and the complete absence of any evidence for advanced civilizations. Given the age of the universe and the rapid pace of technological development, alien civilizations should have had enough time to colonize the entire galaxy many times over. Consider the mathematics. Our galaxy is roughly 100,000 light-years across and 13.6 billion years old. A civilization expanding at just 1% of light speed could colonize every star system in the galaxy within 10 million years. Less than 1/10 of the galaxy's total age. Think of it like releasing a drop of ink into a glass of water. The ink spreads rapidly until it fills the entire glass. Similarly, any technological civilization should spread across the galaxy like a wave, leaving signs of their presence everywhere. Yet, we see nothing. No megastructures, no radio signals, no evidence of stellar engineering or cosmic construction projects. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors like the rate of star formation, the fraction of stars with planets, and the probability that life develops intelligence. Even conservative estimates suggest that thousands of advanced civilizations should exist within our galaxy alone, but the universe appears suspiciously empty. The cosmic microwave background radiation shows no signs of modification by advanced aliens. No stars show the characteristic dimming patterns of Dyson spheres. No gamma-ray signatures indicate antimatter engines. The galaxy seems pristine, untouched by intelligence, except for one small blue planet in an unremarkable solar system. Several explanations have been proposed for this cosmic silence. The Great Filter hypothesis suggests that something prevents life from reaching advanced technological civilization. This filter could be the origin of life itself, the development of complex cells, the evolution of intelligence, or the transition to a spacefaring capability. Perhaps most disturbing is the possibility that the Great Filter lies ahead of us. Advanced civilizations might inevitably destroy themselves through nuclear war, environmental collapse, artificial intelligence, or other technological catastrophes before they can spread beyond their home systems. Alternatively, advanced aliens might be hiding deliberately. They could use stealth technology that makes their activities invisible to our primitive sensors. Or they might operate in dimensions or energy spectra we haven't learned to detect. They might even be present in our solar system right now, observing humanity from locations we never think to examine. The zoo hypothesis proposes that Earth exists within a kind of cosmic nature preserve, maintained by advanced civilizations. These aliens might have agreed to leave primitive species like ourselves undisturbed, while they conduct their business on scales too large for us to comprehend. Some scientists suggest that intelligence naturally turns inward rather than outward as it advances. Instead of building starships and megastructures, advanced civilizations might focus on creating increasingly sophisticated virtual realities, or uploading their consciousness into compact computer systems that require minimal energy. The recent discovery of potentially habitable exoplanets makes the paradox even more puzzling. We now know that Earth-like worlds are common throughout the galaxy. The raw materials for life and intelligence seem to be everywhere. Yet, the products of that intelligence remain stubbornly absent from our observations. Perhaps we're looking in the wrong places or asking the wrong questions. Advanced civilizations might communicate using quantum entanglement, gravitational waves, or other phenomena we're only beginning to understand. Their presence might be obvious once we develop the right tools to see it. The answer to the Fermi paradox will fundamentally shape humanity's cosmic future. If we're alone, we bear the responsibility of spreading life and intelligence throughout an empty universe. If we're not alone, we must prepare for contact with minds that may be as far beyond us as we are beyond bacteria. Life might be the universe's greatest hitchhiker, spreading from world to world on cosmic winds and riding meteorites across the dark between stars. Panspermia. The theory that life spreads throughout the universe via comets, asteroids, and other celestial bodies offers a radical explanation for how biology conquers the cosmos. Instead of originating independently on every world, life might have a single common ancestor that traveled between planets, seeding the galaxy with the building blocks of consciousness. We know that rocks regularly travel between planets in our solar system. Meteorite impacts on Mars blast debris into space, some of which eventually falls to Earth as Martian meteorites. Scientists have found over 200 confirmed rocks from Mars in terrestrial collections, proving that natural processes can transport material across millions of miles of space. Think of these meteorites like interplanetary spore capsules, carrying microscopic passengers on journeys lasting millions of years. The vacuum of space provides perfect preservation conditions, no oxygen to cause decay, no water to break down organic compounds, and radiation levels that might actually help preserve biological materials through a process called radiation-induced polymerization. Some bacteria and other microorganisms show remarkable resistance to the harsh conditions of space. Tardigrades, microscopic animals also called water bears, can survive decades in the vacuum of space, withstanding radiation levels that would kill humans instantly. When rehydrated, they resume normal activity as if nothing happened. Experiments on the International Space Station have exposed various microorganisms to the space environment for extended periods. Many survive the experience, and some even reproduce more rapidly in microgravity conditions. These findings suggest that life could potentially survive interplanetary journeys of months or years. But interstellar panspermia presents much greater challenges. The journey between star systems takes millions of years, even for the fastest moving objects. Cosmic radiation, temperature extremes, and the simple passage of time would test the limits of any biological preservation system. Some researchers propose that life spreads not as living organisms, but as complex organic molecules that serve as templates for new life on suitable worlds. These molecular blueprints could survive interstellar journeys while retaining enough information to bootstrap evolution on planets with the right conditions. Directed panspermia suggests that advanced civilizations intentionally spread life throughout the galaxy by launching biological payloads toward promising star systems. These alien gardeners might use self-replicating probes to distribute genetic material, creating a galaxy-wide network of related biospheres. If panspermia is real, it could explain the apparent speed with which life appeared on early Earth, rather than requiring billions of years to evolve from scratch. Terrestrial life might have started with a head start provided by genetic material from older civilizations. The theory also offers hope for finding life elsewhere in our solar system. If Earth life originated from interplanetary exchange, then Mars, Europa, Enceladus, and other worlds might harbor organisms related to terrestrial biology. We might discover that we have cosmic cousins living beneath the ice of Jupiter's moons. Advanced civilizations might use directed panspermia as a form of cosmic insurance, spreading their genetic heritage across thousands of worlds to ensure their survival, even if their home planet is destroyed. The galaxy could be filled with the descendants of long-dead civilizations, their biological legacy preserved in the genes of countless species. DNA analysis of extremophile organisms on Earth sometimes reveals genetic sequences that seem too complex to have evolved in terrestrial environments alone. These biological signatures might be echoes of our cosmic origins, genetic postcards from civilizations that seeded our world billions of years ago. Just as planets have habitable zones around their stars where liquid water can exist, galaxies have habitable zones where complex life can develop and survive. Too close to the galactic center, and deadly radiation from black holes and supernovae sterilizes entire regions. Too far toward the outer edges, and there aren't enough heavy elements to build planets capable of supporting life. Our solar system sits in what astronomers call the galactic Goldilocks zone, roughly 26,000 light-years from the center of the Milky Way. This seemingly unremarkable location provides the perfect balance of safety and resources needed for billions of years of stable evolution. Think of the galaxy like a cosmic city with distinct neighborhoods. The downtown core, around the central black hole, is densely packed with ancient stars, frequent supernovae, and radiation levels that would cook any planet. The outer suburbs lack the heavy elements needed to build rocky worlds. But the middle suburbs, where we live, offer the perfect combination of safety and amenities. The galactic center contains a supermassive black hole weighing 4 million times more than our sun. This monster occasionally feeds on nearby stars and gas clouds, producing jets of high-energy particles that stream outward for thousands of light-years. Any civilization unlucky enough to be caught in these cosmic searchlights would be sterilized by radiation doses millions of times higher than lethal levels. Star formation in the galactic core creates stellar nurseries where massive stars live fast and die young in spectacular supernova explosions. These stellar death throes release gamma rays and cosmic particles that would strip away planetary atmospheres and destroy the complex chemistry needed for life. But the outer regions of the galaxy present their own challenges. Stars in the galactic halo formed when the universe was young and contained almost no elements heavier than hydrogen and helium. These metal-poor stars cannot form rocky planets or support the complex chemistry that carbon-based life requires. Earth sits in a cosmic sweet spot where star formation has been active long enough to produce heavy elements through stellar nucleosynthesis, but not so active that frequent supernovae make the neighborhood uninhabitable. Our region has experienced relatively few galaxy-scale catastrophes over the past 4 billion years. The galactic habitable zone changes over time as star formation rates shift and the heavy element content of different regions evolves. Areas that are uninhabitable today might become prime real estate in a billion years, while currently safe regions might become cosmic dead zones. Recent research suggests that spiral arms might play a crucial role in galactic habitability. These structures trigger waves of star formation that could disrupt planetary systems through gravitational perturbations. But they also concentrate the heavy elements needed for rocky planet formation. Our solar system appears to have a fortunate orbital pattern that keeps it between the spiral arms most of the time, avoiding the worst effects of these stellar traffic jams while still benefiting from their element-enriching effects. Advanced civilizations might deliberately choose star systems in optimal galactic locations for their long-term expansion efforts. They could wait for spiral arms to pass before establishing colonies, or use stellar engineering to move their entire solar systems to safer neighborhoods. While our sun will burn out in 5 billion years, there are stars so frugal with their fuel that they'll keep shining for trillions of years, longer than the current universe has existed. Red dwarf stars, the smallest and coolest stars in the galaxy, represent humanity's best bet for true long-term survival. These cosmic miser stars burn hydrogen so slowly and efficiently that they'll continue generating energy long after larger stars like our sun have exhausted their fuel and died. Stars like Proxima Centauri, our nearest neighbor, weigh only about 12% as much as the sun, but will live roughly 1,000 times longer. While our sun has perhaps 5 billion years of stable hydrogen burning left, red dwarfs will continue shining for 6 to 12 trillion years. Time enough for evolution to restart from bacteria and produce entirely new forms of intelligent life. Think of red dwarfs like hybrid cars compared to gas-guzzling trucks. They burn their fuel so efficiently that even the smallest red dwarf will outlive every other type of star in the galaxy. When the last massive stars have exploded as supernovae and the medium-sized stars have puffed away their outer layers, red dwarfs will still be quietly converting hydrogen to helium. The galaxy contains roughly 75% red dwarf stars, making them by far the most common stellar type. Within 50 light-years, there are over 100 red dwarfs, many of which likely host planetary systems. These dim stars offer humanity hundreds of potential destinations for interstellar colonization. But living around a red dwarf requires adaptations that would fundamentally change human civilization. These stars produce only a fraction of the energy output of our sun, meaning that habitable planets must orbit much closer to stay warm enough for liquid water. A planet in the habitable zone around a red dwarf might have an orbital period of just a few weeks. The close orbital distances create a phenomenon called tidal locking, where one side of the planet always faces the star, while the other side remains in permanent darkness. The day side would experience eternal noon with temperatures hot enough to boil water, while the night side would be colder than Antarctica. Between these extremes lies the terminator zone, the twilight boundary where temperatures might allow liquid water and possibly life. Colonies on tidally locked worlds would need to be built in this narrow band, where an eternal sunset provides just enough warmth for human survival. Red dwarf planets face another challenge. These stars frequently produce powerful solar flares that could strip away planetary atmospheres over millions of years. However, planets with strong magnetic fields or thick atmospheres might be able to resist this erosion and maintain habitable conditions. The dim red light from these stars would require fundamental changes to any Earth-based agriculture. Plants would need to adapt to near-infrared wavelengths, creating alien forests that appear black to human eyes but efficiently harvest the available starlight. Despite these challenges, red dwarf systems offer unprecedented stability. Once a red dwarf reaches its main sequence phase, It can burn steadily for trillions of years without significant changes in brightness or energy output. Civilizations established around these stars could literally outlive the universe as we know it. Drifting through the darkness between stars are worlds without suns, ejected from their birth systems to wander the galaxy as cosmic orphans, carrying hidden oceans beneath frozen shells. Rogue planets, also called free-floating planets, exist in interstellar space without orbiting any star. These wandering worlds were either ejected from their original solar systems during chaotic early formation periods or formed independently in the dark clouds between stars. Astronomers estimate that our galaxy contains billions or even trillions of rogue planets, potentially outnumbering star-bound worlds by factors of hundreds or thousands. These invisible wanderers drift through space at speeds of dozens of miles per second, following the gravitational currents of the galaxy on journeys lasting billions of years. Think of rogue planets like cosmic icebergs floating in an ocean of darkness. Without a star's warmth, their surfaces freeze to temperatures approaching absolute zero. Any atmosphere they once possessed would condense and fall as snow, creating landscapes of frozen nitrogen, oxygen, and carbon dioxide under skies as black as the void. But beneath these frozen surfaces, some rogue planets might harbor conditions suitable for life. Planets with thick atmospheres or substantial radioactive decay in their cores could maintain liquid oceans beneath miles of ice. These hidden seas might remain warm for billions of years, powered by geothermal energy instead of starlight. Jupiter-sized rogue planets could generate enough internal heat through gravitational compression to keep vast oceans liquid for longer than the current age of the universe. These wandering water worlds might support complex ecosystems based on chemosynthesis rather than photosynthesis, similar to the life forms around Earth's deep-sea hydrothermal vents. Some rogue planets might have been ejected from their home systems along with captured moons. A large rogue planet with multiple moons could maintain a complex gravitational system in interstellar space, with tidal heating keeping the moons geologically active and potentially habitable for billions of years. The detection of rogue planets presents enormous challenges, since they emit almost no light and can only be found through their gravitational effects. Astronomers use a technique called gravitational microlensing, where a rogue planet's gravity briefly magnifies the light from a background star as it passes between the star and Earth. Recent surveys suggest that rogue planets might be surprisingly common. Some estimates indicate that for every star in the galaxy, there might be 2 or more free-floating planets wandering the interstellar medium. This would mean trillions of hidden worlds drifting unseen through the cosmic dark. Advanced civilizations might deliberately eject planets from their home systems as a form of cosmic colonization. By giving worlds the right gravitational kick, they could send inhabited planets on interstellar journeys lasting millions of years, spreading life throughout the galaxy on a timescale much longer than spacecraft travel. Rogue planets could serve as stepping stones for interstellar exploration. Instead of making the full journey to another star system in one leap, spacecraft could hopscotch between rogue planets, using them as refueling stations and waypoints on much longer journeys. 13.8 billion years from now, when the last star flickers out and the final black hole evaporates, the universe will reach a state of maximum entropy, where no more work can be done and time itself becomes meaningless. The heat, death of the universe represents the ultimate deadline for all conscious beings. According to the laws of thermodynamics, energy constantly flows from hot to cold, and this process cannot be reversed without adding more energy from somewhere else. Eventually, the universe will reach thermal equilibrium, where no energy gradients exist to power stars, planets, or life. This cosmic endgame unfolds over timescales that dwarf human comprehension. In roughly 5 billion years, our sun will exhaust its hydrogen fuel and expand into a red giant, vaporizing Earth's oceans and atmosphere. But this represents just the opening notes of a symphony of destruction that will play for trillions upon trillions of years. Think of the universe like a giant clock spring that was wound up during the Big Bang and has been unwinding ever since. The expansion of space, the formation of galaxies, the birth and death of stars, all of these processes represent energy flowing from concentrated forms to dispersed forms, bringing us closer to the final state of equilibrium. In 100 trillion years, star formation will cease as galaxies exhaust their gas supplies. The universe will enter what astronomers call the degenerate era, populated only by white dwarfs, neutron stars, and black holes, slowly cooling in the expanding darkness. But even these stellar corpses won't last forever. Protons, the fundamental building blocks of ordinary matter, may decay with a half-life of roughly 10 to the 34th power years. If this prediction proves correct, all atoms will eventually disintegrate, leaving behind only electrons, positrons, neutrinos, and photons in an increasingly dilute cosmic soup. Black holes, the most long-lived objects in the universe, will persist long after protons decay. But even they cannot escape thermodynamics. Stephen Hawking discovered that black holes slowly evaporate by emitting radiation, with the largest holes taking roughly 10 to the 100th power years to completely disappear. The final era of the universe will be dominated by an increasingly thin gas of elementary particles and photons with temperatures approaching absolute zero. No complex structures can exist in this environment. No chemistry, no biology, no consciousness. Just elementary particles drifting apart in an ever-expanding void. Yet, some theoretical physicists propose ways that intelligence might survive even this ultimate catastrophe. Advanced civilizations could potentially harness the energy from proton decay or black hole evaporation to power incredibly efficient computers. These systems could run conscious minds at such slow speeds that subjective time extends indefinitely, even as the universe grows cold. Alternative scenarios include vacuum decay, where the fundamental properties of space itself change catastrophically, or the Big Rip, where dark energy acceleration eventually tears apart molecules, atoms, and even elementary particles. Both possibilities would end consciousness more quickly than heat death, but are considered less likely based on current observations. Some cosmologists speculate about cyclic universe models, where the current expansion phase eventually reverses, leading to a big crunch that could restart the cosmic cycle. In such models, intelligence might find ways to encode information that survives the transition from one universe to the next. The heat-death scenario assumes that the laws of physics as we understand them remain constant throughout cosmic time. But if consciousness can modify physical laws or discover new sources of energy, the ultimate fate of intelligence might be very different from what thermodynamics predicts. For humanity's immediate future, heat death provides crucial perspective on our cosmic significance. We exist during a brief window when the universe contains enough organized energy to support complex structures like stars, planets, and life. The choice facing humanity is simple, yet profound. Evolve into a cosmic civilization capable of surviving the death of stars, or remain forever trapped on a single world, awaiting extinction. Becoming a truly spacefaring species requires more than just building better rockets or developing faster propulsion systems. It demands a fundamental transformation of human consciousness, biology, and social organization. We must evolve from planetary creatures into beings capable of thriving in environments that would instantly kill any Earth-born organism. The transition will happen in stages, each representing a quantum leap in our capabilities and our cosmic perspective. First comes the mastery of our own solar system, establishing self-sustaining colonies on Mars, mining asteroids for resources, and building rotating habitats in space. This phase could begin within the next century if we maintain our current rate of technological progress. Think of this first phase like learning to walk before we can run. We need to prove that humans can live and reproduce in space environments, develop closed-loop life support systems that work for decades, and create technologies for manufacturing everything we need using space-based resources. The second phase involves reaching nearby star systems using whatever propulsion technology we can develop. Whether through generation ships, fusion rockets, or exotic physics we haven't discovered yet. The first interstellar colonies will mark humanity's transition from a single-world species to a multi-system civilization. But the real transformation happens in the third phase, when human settlements become self-sustaining across multiple star systems. At this point, we achieve true cosmic redundancy. No single catastrophe can eliminate our species. We become immune to asteroid impacts, supervolcano eruptions, gamma-ray bursts, and even the death of our home star. This distributed civilization would need to develop new forms of government, economics, and communication adapted to the vast distances between worlds. A message sent from Earth to Proxima Centauri takes 4.25 years to arrive. Building consensus across interstellar distances requires patience and planning on scales no human society has ever achieved. Advanced spacefaring civilizations might barely resemble modern humans. Genetic engineering could adapt our bodies to different gravity levels, radiation environments, and atmospheric compositions. Cybernetic enhancements might allow a direct interface with spacecraft systems. Digital consciousness could enable exploration of environments too dangerous for biological bodies. The energy requirements for a true cosmic civilization dwarf anything we can currently imagine. Building Dyson spheres, accelerating generation ships to significant fractions of light speed. And terraforming entire worlds requires power sources on stellar scales. Mastering fusion, antimatter, or other exotic energy sources becomes essential for cosmic-level projects. Perhaps most importantly, becoming spacefaring means accepting the responsibility for preserving and spreading life throughout the universe. We might be the only conscious beings in our cosmic neighborhood, making us the custodians of billions of years of evolution. Our expansion could determine whether intelligence survives and flourishes among the stars. The alternative is sobering. Every species that remains bound to a single world eventually faces extinction. Stars die, planets become uninhabitable, and cosmic catastrophes reset the evolutionary clock. Without spaceflight, consciousness itself might be nothing more than a brief flicker in an otherwise lifeless universe. But if we succeed in spreading beyond Earth, we could become something unprecedented in cosmic history, a species that outlives the stars themselves. Our descendants might witness the formation and destruction of galaxies, guide the evolution of life throughout the cosmos, and possibly even survive the heat death of the universe itself. The journey from a planetary to a cosmic civilization represents the next great chapter in human evolution. We stand at the threshold of this transformation, with the technology to begin serious interstellar exploration within our lifetimes. The question isn't whether we can leave our solar system. The question is whether we have the wisdom and determination to become worthy of the stars.
Space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemists, but that's just peanuts to space. Douglas Adams wrote that, and it's funny until it's not. Because once you let that line really sink in, something strange happens. You stop laughing. You feel it tug at the edges of your reality, like your mind just bumped into a wall it didn't know was there. Tonight, we're going to push straight through that wall. This is not just a video, it's a journey. A slow, expanding meditation on one simple, impossible question: how big is the universe? Not in numbers, not in statistics, but in something you can actually feel. Because if the universe really is as big as we say it is, if it's growing faster than the speed of light, if it holds trillions of galaxies, each with hundreds of billions of stars, if it's been around for nearly 14 billion years, then what does that make you? What does that make your life, your problems, your plans, your breath? Over the next few minutes, we're going to zoom out farther than your brain wants to go, farther than it can go, at least without breaking a little. We'll begin with the ancient stargazers, move through early telescopes, modern science, and the invisible edges of the observable cosmos. But we'll also dive into the emotional fallout of confronting scale, because numbers are cold, perspective is personal. If you feel your sense of self start to dissolve, if something inside you stirs with awe, or fear, or wonder, then you are on the right path. Now, take a second, look around the room you're in, the walls, the furniture, the objects you own, the planet spinning beneath you. All of that exists inside a galaxy, spinning inside a filament stretched across a universe that's expanding so fast, light itself can't keep up. And we're going to trace it all, one part at a time. In the beginning, there was light, but before that, there was silence. Let's begin. There's something visceral about standing under a truly dark sky, without streetlights or building glow. The Milky Way spills overhead like a river of diamonds, each star twinkling with age and distance. In that moment, you might feel your pulse slow, your usual concerns dissolve, and a quiet clarity take their place. Psychologists have a name for this feeling: awe. It is an intense emotional state where your sense of self shrinks and your sense of connectedness expands. It's more than poetic, it's physiological. Blood pressure lowers, the heart calms, and stress retreats into the shadows. This feeling is no coincidence. Researchers have found that this emotion triggers the release of calming hormones, quiets the internal chatter of the mind, and even lowers markers of inflammation. In studies, people who regularly seek out awe through stargazing or natural beauty report less anxiety, more happiness, and a deeper sense of meaning. And it isn't limited to remote wilderness. Just a few minutes gazing at rooftops and city stars can still spark the same mental shift. This emotional release is essential when we approach cosmic scale. When we begin to discuss light years and galaxies, our brains need to unclench. If your mind is stuck in daily stress, the numbers bounce off your awareness like static. But in this calm openness, each figure becomes a revelation. You start to breathe with the universe. That's why this part of our journey isn't about measurements or history. It's a ritual. It's preparing your heart and mind to receive the grandeur at the core of this journey. As you sink into that awe, your world shrinks your clothes, your commute, your arguments into a silent backdrop, and the cosmos opens. This resets anything that stood between you and wonder. Now, you're not just watching a video, you're stepping onto a shared platform of astonishment. From here, every cosmic revelation will resonate deeper. You'll not only understand the scale, you'll feel it. In the early 1800s, the cosmos still whispered its secrets without revealing its scale. Telescopes had sharpened our view, but the true distances to stars remained elusive. How could anyone grasp light years using nothing more than geometry and patience? Enter Friedrich Bessel, a methodical German astronomer. Around 1837 to 1838, he turned a powerful new instrument, the Fraunhofer heliometer, toward a faint, fast-moving star called 61 Cygni. With this precise device, he measured tiny shifts in the star's position caused by Earth's orbit, an effect known as parallax. Imagine measuring an object so distant that its shift mirrors the movement of a tiny coin seen from miles away. Bessel logged over 100 careful observations across seasons. By comparing the star's position against distant background stars, he detected a minute wobble, just a few hundredths of an arcsecond. From that, he calculated a distance of about 10.4 light-years, an astonishing first. The universe now had a measure. Soon after, other astronomers confirmed stellar distances. Thomas Henderson measured Alpha Centauri from South Africa, and Wilhelm Struve charted Vega. But it was Bessel's parallax of 61 Cygni that set the cosmic scale firmly into human hands. This wasn't just data, it was a portal. Triangles and patience transformed the night sky into a quantifiable domain. Suddenly, distances once imagined became numbers, still vast, but within the grasp of human minds. That foundational feat, measuring one star, paved the way for astronomers to build longer ladders. From nearby stars, they would ascend through techniques like Cepheid variables, supernovae, and redshift. Each rung would push us farther into the deep cosmos. But for now, this is where it began, with Bessel's quiet persistence under Königsberg skies, defying human intuition. He taught the world that cosmic distances could be known, bridging empty space with geometry and resolve. Building on Bessel's breakthrough, astronomers realized they needed a brighter, more distant ruler to reach galaxies beyond our Milky Way. That ruler came in the form of Cepheid variable stars, pulsating beacons whose brightness flips on a reliable rhythm. These stars, discovered in the late 19th century, pulsate with a period directly tied to their intrinsic brightness. Measure how fast they brighten and dim, and you can deduce their true luminosity. Then, compare that with how bright they appear, and voila, you get their distance. In the 1920s, Edwin Hubble used this technique to resolve a cosmic mystery, the nature of nebulae like Andromeda, by spotting Cepheids in Andromeda and calculating their distance. He showed that these nebulae were not part of our galaxy. They were entire galaxies themselves, each containing billions of stars. That meant the universe was exponentially larger than anyone had imagined. This was a revolution. We went from knowing distances to a handful of nearby stars to gauging entire galaxies millions of light years away. Cepheid variables, with their rhythmic pulse and predictable luminosity, became the second rung on the cosmic distance ladder, lifted by Bessel's first geometric step. As we peer deeper, we realize the universe isn't just vast. It's populated with countless cities of stars. Each Cepheid lights the path, anchoring distant galaxies to our expanding cosmic map. This new sense of scale brought with it a new sense of loneliness, and a new sense of wonder. We were no longer at the center of a single stellar island, but adrift in an archipelago of galaxies, each one a universe unto itself. The night sky became a deep ocean, and we had just learned to build the first lighthouses to navigate its shores. After Cepheid variables lit the path to nearby galaxies, astronomers faced a new challenge, measuring distances to galaxies so far away that no individual stars could be resolved. For that, they needed something brighter, something explosive. That something was the Type Ia supernova. These aren't ordinary stars. They are detonations. White dwarf stars in binary systems that steal matter from their companions until they reach a critical tipping point. When that limit is exceeded, the star collapses inward and then detonates with unimaginable force. The explosion is so bright it can be seen across billions of light years, often outshining an entire galaxy for weeks. But the most useful part, these explosions are reliably similar in brightness. Nature, it seems, gave us a cosmic flashlight. Because Type Ia supernovae explode under nearly identical conditions, they reach a nearly uniform peak brightness. This makes them perfect standard candles. Once astronomers know how bright the explosion should be, they compare it to how bright it appears from Earth. The difference tells them how far away the explosion happened. The brilliance of this method is that it extends our reach. We're no longer limited to our galactic neighborhood. With these supernovae, we can measure distances to galaxies billions of light years away, galaxies too distant and dim for even our best telescopes to resolve in detail. But there's more. These supernovae don't just give us distances. They tell us something deeper about motion. When astronomers charted the distance to many of these galaxies, they realized something shocking: the farther away a galaxy is, the faster it appears to be moving away from us. This relationship, distance and velocity, is the fingerprint of an expanding universe. It's what led to the formulation of Hubble's law. The universe isn't just vast, it's growing vaster with time. That realization shook the foundations of physics. The cosmos is not static, it's dynamic, stretching, growing, evolving. Every supernova flash, every measured distance, is a note in the grand song of expansion. This part of our journey changes the tone. We are no longer bound to a finite sky. The universe is not just big, it's becoming bigger. The stars are not fixed in a dome. They are hurtling away from one another in a silent, accelerating ballet. This is where the comfortable feeling of awe begins to mix with a sense of cosmic vertigo. The ground beneath our understanding of reality has started to shift, and the universe is pulling away from us in all directions at once. For decades, astronomers believed the universe expanded in the aftermath of the Big Bang, but the force of gravity would eventually slow that growth, maybe even cause it to reverse. That made sense. Every explosion eventually settles. Every stretch pulled by weight should strain and sag, but something wasn't adding up. When scientists used Type Ia supernovae to measure the distances and velocities of extremely remote galaxies, they noticed a terrifying detail. The farthest galaxies weren't just moving away, they were accelerating. The deeper you looked into space, the faster galaxies seemed to retreat, not in a straight line, not in a steady drift, but in a runaway expansion, as if space itself were being pulled apart by some invisible force. This revelation struck like lightning. The universe wasn't slowing down, it was speeding up. What could possibly be pushing galaxies apart faster and faster? It wasn't gravity. It wasn't matter. It was something else. Something that didn't cluster, didn't shine, didn't slow. It became known as dark energy, not because it's related to darkness, but because we have no idea what it really is. Imagine blowing up a balloon, expecting the stretch to ease, only to find it stretching faster with each breath. That's what dark energy is doing to space. Not only between galaxies, but between superclusters, between vast voids. It's not just carrying galaxies away, it's creating more space between them, making the distances unbridgeable. And here's the strangest part. Dark energy doesn't seem to weaken. It doesn't dilute as the universe grows. It persists. In fact, it dominates. Today, astronomers estimate that nearly 70% of the entire energy in the universe is this invisible accelerant. The stars, planets, dust, everything we can touch or see makes up less than 5%. Let that sink in. Almost all of reality, by volume and by force, is made of something we cannot touch, see, or fully explain. And yet, it defines our fate. This is the moment in our journey where awe turns to something deeper, unsettling, curiosity. If everything is moving away from everything else, faster and faster, what happens in the end? Will galaxies one day slip beyond our view? Will stars wink out forever? Will the sky grow dark, not from lack of stars, but from unbridgeable space? We're not just measuring distance anymore, we're measuring destiny. Once we realized the universe was expanding and accelerating, the next question was chillingly simple. How does this end? To even guess, we first have to understand how space itself might be shaped. It's easy to imagine the universe as a giant balloon or an endless plane, but space is more complex than any surface we can draw. Its shape isn't just geometry, it's destiny. Physicists broke it down into 3 possible forms: flat, open, or closed. If the universe is flat, like an endless sheet, expansion can continue forever, slowing but never stopping. If it's open, like a saddle curving outward, it will also expand eternally, only faster. But if it's closed, like a sphere, expansion might one day halt and reverse, pulling everything back together in a fiery collapse, the Big Crunch. For years, no one knew which shape we lived in, but thanks to precision measurements of ancient light, the cosmic microwave background, we now believe the universe is incredibly close to flat. Not perfectly, but within such fine margins that for all practical purposes, it stretches out endlessly in all directions. That would mean no edges, no center, just more space forever. But flatness doesn't mean comfort, because the accelerating expansion means this flat universe is ruled by dark energy, and that changes everything. Imagine a universe where every second, more distance appears between galaxies, where light itself gets stretched until it fades, where stars drift so far apart that they vanish from each other's skies. In the far future, entire galaxies will slip beyond our cosmic horizon, disappearing from view forever, not because they're moving too fast, but because space is growing so rapidly between us that their light will never reach us again. Eventually, only the closest galaxies, perhaps just our local group, will remain visible. The rest will vanish into silence. This possible fate is called the heat death, a slow fade into cold, empty space, no explosions, no collapse, just distance, infinite distance. Every particle spreads so far from the next that interaction becomes impossible. Even black holes evaporate, even light forgets. It's a fate not marked by chaos, but by stillness. But there are other theories. Some believe dark energy might grow stronger, eventually tearing apart not just galaxies, but stars, planets, atoms themselves. This is the Big Rip. Others think dark energy may decay or reverse, creating cycles of expansion and collapse. Right now, we don't know. But what we do know is the shape of the universe and the force driving it apart is not just theoretical. It will determine how time ends. The numbers may say 13.8 billion years, but that's not a time any of us can grasp. It's a concept that lives outside our normal experience. When we say the beginning of the universe, it feels like we're talking about a moment, like an explosion you could have witnessed if only you were there. But this wasn't a moment within space. It was the moment space began. There was no outside to witness it, no edge. It emerged from no before, just emergence. The Big Bang wasn't an explosion in space. It was an explosion of space. Every atom, every point of matter, every law of physics was born in that flash. At first, there were no stars, no galaxies, not even atoms. Just a searing soup of energy hotter than anything the human brain can truly picture. The entire observable universe, now stretched over 93 billion light years, was once smaller than a single grain of sand, and in that grain, time ticked its first seconds. In less than a heartbeat, the universe underwent a phase called inflation, a fraction of a second where it expanded faster than the speed of light, not in violation of physics, but because space itself has no speed limit. That inflation set the scale of the cosmos. It smoothed the wrinkles, shaped the patterns, and blew quantum fluctuations into the seeds of galaxies. Then came cooling. In the first 3 minutes, protons and neutrons formed hydrogen, helium, the basic elements of everything we know. Matter began to assemble, gravity began its pull, and slowly, after nearly 400,000 years of darkness, the universe became transparent. Light could move freely for the first time. That first light is still out there, whispering in microwaves, faint but eternal. From that point, structures began to form. Clouds of gas collapsed into stars. Stars gathered into galaxies. Galaxies spiraled and danced and collided. From fire, form, from chaos, architecture, billions of years passed. In one quiet corner, a small star formed, orbited by dust and rocks. One of those rocks grew oceans, life, minds, eyes that would look back and ask, where did we come from? And the answer is from that beginning. From heat, gravity, and time, from nothing came everything. It wasn't random, but it wasn't planned. It was natural law unfolding at unimaginable scale. And even now, every particle in your body carries a history that began in that moment. Every breath you take is made of atoms forged in the early fire. You are the residue of that great beginning. In the early universe, after the Big Bang's blaze cooled into darkness, there were no stars, just a vast, silent expanse of hydrogen and helium gas. Gravity waited patiently. And then, millions of years after that first light broke free, clumps began to form. Tiny, irregular densities, amplified by gravity, drew gas inward. The universe took its first breath of structure. These clumps collapsed, and when they did, the first stars were born. But these weren't stars like the ones we see now. They were giants, monsters by comparison, dozens or even hundreds of times more massive than our sun, burning with a brilliance we can scarcely imagine. They lived fast and died young, some surviving just a few million years, mere sparks in cosmic time. We call them population 3 stars, the hypothetical first generation. They were made from pure hydrogen and helium, the original elements created in the Big Bang. No carbon, no oxygen, no metals. In the language of astronomy, metals means anything heavier than helium, and these stars had none. They were truly primordial. Because of their massive size, these stars burned furiously. Their cores fused hydrogen into helium, then helium into heavier elements. But their weight was their doom. Many ended their lives in cataclysmic supernovae or collapsed directly into black holes. They left behind no fossil record, no glowing remnants, only their ashes, scattered as heavier elements across the cosmos. And it is from those ashes that everything else formed. The carbon in your body, the iron in your blood, the oxygen you breathe, none of it existed before those stars. They built the ingredients of life in their fiery deaths. Without them, no planet would ever support life, no tree would ever grow, no thinking creature would ever stare upward and wonder. We have never seen one of these first stars. They died too long ago, too far away. Their light may have faded, or their remnants may lie hidden in ancient galaxies, cloaked by dust and distance. But we can infer their existence by what came after newer generations of stars filled with heavy elements. Galaxies laced with dust, planets rich with complex chemistry. They were the universe's first alchemists, and the mystery remains. Are any of them still out there? Could a small one have survived to this day, ancient and quiet, orbiting in some forgotten region of space? If so, it would be older than any known star, a relic from a time before structure, before light, before the universe we now know began to take shape. Once the first stars lived and died, the universe entered a new era. It was no longer just a sea of gas. It had history, it had heavy elements, and it had a sculptor gravity. Gravity doesn't rush, it waits, pulls, builds. Over hundreds of millions of years, tiny clusters of stars merged, collided, and grew. What began as loose gatherings of starlight eventually became galaxies, vast, spinning cities of stars, each one a gravitational cathedral built from the wreckage of stellar lives. Galaxies didn't appear all at once. They emerged slowly through collision and cooperation. Early galaxies were chaotic, irregular shapes, small groups of stars with no symmetry, but gravity had time. Billions of years passed, smaller galaxies merged, drawn into larger spirals and ellipses. Collisions weren't destructive, they were creative. Galaxies grew by devouring each other. Our own Milky Way is a product of that process. It wasn't born fully formed, it's the result of countless mergers, each one adding stars, dust, and structure. Even today, it's still growing. Our galaxy is in the process of absorbing smaller companions, like the Sagittarius dwarf galaxy. The dance never ends. Step back for a moment. Imagine flying above the cosmos. Below you, hundreds of billions of galaxies, each containing hundreds of billions of stars. Some spiral like pinwheels, others form giant ellipses. Still others are chaotic blobs. These aren't just isolated structures. They form vast networks, connected by invisible threads of gravity and dark matter. Galaxies don't float randomly. They align into filaments, forming the cosmic web, a vast lattice of matter stretching across the universe. In between, immense voids, places where nothing shines, where darkness reigns. This structure is breathtaking. It resembles neurons. High-speed simulations of the cosmic web look eerily like brain scans. Billions of galaxies arranged in patterns that mirror our own thoughts. Perhaps it's a coincidence, perhaps not. Inside galaxies, stars form in waves. Gas clouds collapse under their own weight, giving birth to stellar nurseries. Bright blue, short-lived stars blaze to life, illuminating spiral arms. Over time, the balance shifts. New stars form less frequently. Galaxies settle into quiet maturity. Some galaxies remain small, peaceful, drifting alone. Others collide, massive, slow-motion encounters that stretch over billions of years. When that happens, stars rarely collide directly. They're too far apart. But their gravitational interactions reshape everything, triggering waves of star formation, distorting arms, merging black holes. And one day, we will witness this firsthand. The Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, they will begin to merge, not in violence, but in beauty. The night sky will fill with new arcs of stars. The galaxies will wrap around each other in a glowing spiral, and eventually, they will become one. This is the destiny of galaxies, not isolation, but union. The cosmos builds through collision. It sculpts order from motion, and what began as scattered starlight becomes structure. The Milky Way. To the naked eye, it's a soft band of light across a dark sky, poetic, serene, familiar. But from above, if you could somehow float beyond its reach, you would see a spiral hundreds of thousands of light years across, rotating like a cosmic whirlpool, 100 billion stars circling a hidden heart. This is our galaxy, our home, a flattened disk of stars, dust, gas, and memory. We reside within one of its spiral arms, the Orion Arm, nestled between two larger ones, Sagittarius and Perseus. That placement, modest and off-center, is a gift. It gives us a clearer view of the galaxy's structure, less interference, more access to the sky beyond. If we had been born in the crowded galactic core, the night sky might have been a blinding wall of starlight, beautiful but obscuring everything else. The Milky Way rotates once every 230 million years. That means the last time the sun was in its current position in this spiral dance, Earth was inhabited by early dinosaurs. Stars like our sun orbit the galactic center at incredible speeds, around 800,000 kilometers per hour. Yet the galaxy is so vast, it takes them hundreds of millions of years to make a single loop. At the heart of the Milky Way lies a mystery, a supermassive black hole. It doesn't consume everything, but it defines the center. Millions of solar masses compressed into a space smaller than our solar system. We can't see it directly, but we see its influence on stars that orbit invisible points, on matter that spirals inward and vanishes, on radiation echoing from its borders. But not all of the Milky Way is dense or dangerous. Much of it is dust and gas, nebulae glowing with starlight, regions where stars are born. In these stellar nurseries, gravity compacts hydrogen until fusion ignites, and new stars emerge. Some live fast and die as supernovae. Others, like our sun, burn steadily for billions of years. We are tethered to this spiral, part of its architecture. The atoms in your body were once scattered across this galaxy, fused in different stars, exploded into space, recycled in molecular clouds, and eventually gathered here into the form you now inhabit. Even now, the Milky Way is not alone. It's surrounded by satellite galaxies, small companions like the large and small Magellanic Clouds, orbiting like children around a parent. It's in motion, pulled toward its neighbors, eventually destined to merge with Andromeda in a titanic fusion of star systems. Yet, we only see a part of it. A vast portion of the Milky Way remains invisible, shrouded in dust, or hidden by the very matter we ride within. And surrounding all of it is a halo of something else, something that doesn't glow but binds everything dark matter. It holds the galaxy together, shaping its rotation, its structure, its survival. The Milky Way is not just a collection of stars, it's a gravitational symphony. It is the pattern that gave rise to planets, oceans, minds, questions. Drifting in one of the Milky Way's spiral arms is a star that doesn't stand out. It's not the brightest, not the biggest. It's young compared to many, a yellow dwarf among billions of others. And yet, everything you've ever known, loved, or imagined exists because of this one ordinary star. We call it the Sun. The Sun formed around 4.6 billion years ago from the collapse of a molecular cloud, just another swirl of hydrogen and dust nudged into motion by gravity and maybe a nearby supernova. As the cloud condensed, its center ignited. Fusion began. A star was born, but the Sun didn't arrive alone. Around it, a flat disk of gas and dust spun into structure. Over millions of years, particles collided and clumped, forming larger and larger bodies, moons, asteroids, planets. 8 of them, along with countless smaller fragments, began orbiting the Sun in orderly ellipses. Earth was one of them. Our planet coalesced from dust and stone, heating under the pressure of its own gravity. Volcanic fury, constant bombardment, a molten beginning. Then, After a catastrophic collision with another protoplanet, Earth gained a moon, a stabilizing presence, a cosmic twin. But Earth wasn't special just because of its geology. It was its distance from the sun, a perfect zone, not too hot, not too cold, that allowed water to remain liquid. And where there's water, chemistry becomes possible. Over time, carbon compounds danced in oceans, struck by lightning, heated by vents, nudged by time, and something emerged. The first cells, life. Single-celled at first, barely more than molecules. Then, complexity, photosynthesis, oxygen, multicellularity, eyes, fins, wings, thought, civilization, all of it powered by the sun. Its energy warmed our seas, fed our plants, drove our weather, lit our skies. Without that constant, distant nuclear fusion, Earth would be an icy, lifeless rock drifting in silence. But zoom out. Our sun is just one among hundreds of billions in our galaxy, and our galaxy is just one among trillions in the universe. If this single, average star could give rise to oceans and mines, what else might be out there? What other stars cradle worlds of their own? What other orbits might carry oceans, continents, life forms staring up at their own stars, wondering if they, too, are alone? The sun is a local engine, but it raises universal questions. Its ordinariness is what makes it extraordinary. Because if something so unremarkable can give rise to thought and emotion, to cities and language, to you and me, then the universe might be bursting with stories, and we've only just begun to listen. For most of history, we believed Earth was unique, the only world, the center of everything. Even after we realized the sun was a star among many, we still clung to the notion that planets were rare, that life, especially intelligent life, was a fluke. But then, everything changed. In the 1990s, astronomers began detecting the first exoplanets, planets orbiting stars beyond our sun. At first, they found giants, massive, bizarre worlds orbiting dangerously close to their stars, scorching gas balls nicknamed hot Jupiters. They were unlike anything in our solar system, exotic but real. And then came more, dozens, hundreds, thousands. Today, we've confirmed over 5,000 exoplanets, with thousands more candidates waiting for confirmation. These aren't just statistical blips, they're everywhere. It turns out that nearly every star in the night sky probably has at least one planet. Many have whole systems, some may have dozens. The techniques used to find them are subtle. We watch stars flicker as planets pass in front of them. We observe the tiny gravitational tugs they exert on their suns. It's like detecting a moth circling a distant street lamp by watching how the light dims for a heartbeat. From these delicate signals, we reconstruct other worlds. Some are gas giants, others are rocky like Earth. A growing number sit in the habitable zone, not too close, not too far from their star, where temperatures could allow liquid water to exist. We call these Goldilocks planets. Not too hot, not too cold, just right. These planets haunt us because every time we find a rocky world orbiting in just the right place, our imagination runs wild. Could it have oceans, weather, life? Could it have evolved minds, cities, stories? Could someone there be looking back, wondering if they, too, are alone? But it's not just romantic fantasy. With instruments like the Kepler Space Telescope, TESS, and soon the James Webb Space Telescope, we're beginning to study atmospheres, to detect the fingerprints of chemistry, water vapor, even oxygen. Soon, we may be able to smell alien skies across the light years. The odds are shifting. Once, we thought we were a cosmic miracle. Now, it's starting to look like the miracle might be the rule, not the exception. Life may not be rare, it may be inevitable, written into the physics of the universe like gravity and light. And if that's true, the silence of the cosmos becomes more profound. Where is everyone? We'll ask that question soon. But first, we need to understand the scale we're working with, because the nearest potentially Earth-like planet might still be 40 light-years away. That's unimaginably close on a galactic scale, and yet impossibly far for us. Now, we've talked about exoplanets, potential Earth-likes, worlds floating in the Goldilocks zone, but now let's get real. How close are they? What do their distances mean? Imagine this: a planet only 40 light years away. That's practically our next-door neighbor on a cosmic scale. But in practical terms, it would take tens of thousands of years, just with today's fastest spacecraft, to get there. 40 years for light, but tens of millennia for steel. And yet, 40 light years is tiny next to the galaxy's size of 100,000 light years across. It's like measuring centimeters on a football field. So, yes, we're practically neighbors in galactic terms, but practically, it's unreachable. Then there are planets 100, 500, 1,000, even thousands of light years away. Their starlight is old news, history arriving decades or centuries after it happened. If you saw something happening there, it might have already ended long ago. Here's the emotional hum: these worlds are near in scale, unimaginable in distance. We can see them, catalog them, study their light, but to touch them is still impossible. This tension, that space can be small and huge, is the heart of cosmic wonder. It's hope steeped in humility. It's the thrill of possibility tempered by reality. And it raises a question: what do we do with that? Do we wait for technology to catch up? Do we beam signals, build telescopes, try to listen? Do we imagine futures where we hop between stars or find meaning right here? Over the next few minutes, in this and upcoming parts, we'll explore those questions. We'll chart the silence between stars. We'll learn what we can know about those distant skies. We'll shine a narrative torch across space-time, possibility. Because as much as numbers describe distance, stories bring it home. We've measured distances, charted orbits, and found thousands of distant worlds. Now comes the real question. How do we look for life? Not just any life, but life as we might recognize it. First, we listen to the stars. Natural light holds secrets, fingerprints of molecules in alien atmospheres. With powerful telescopes, we analyze absorption spectra, hunting for biosignatures: oxygen, methane, water vapor. A whiff of oxygen may mean photosynthesis. Paired with methane, that's a chemical imbalance often linked to life processes. Then, there's the search for technosignatures, a fancy term for alien technology, signals, structures, energy use, anything that points to intelligence. The SETI projects have scanned the skies for decades, listening for narrowband, repeating pulses, signs of radio transmissions or beacon signals. No definitive finds yet, but the search has only just begun. Closer to home, our probes and rovers dig into Mars, search for plumes on Europa's icy surface, and plan missions to Titan. They hunt for microbial fossils, subsurface oceans, and organic chemistry, the precursors or evidence of life. Each of these efforts is a step toward understanding our place. We're not just asking, is there life out there? We're asking, what does it mean if the universe is teeming with life, even microbial, or if we're truly alone? The answer changes everything. If life is common, then a spark of biology connects every world with it. Evolution becomes a universal story, not a fluke. If we're alone, then every living soul, every tree, every ocean on Earth becomes a priceless cosmic anomaly. Whether we find life or not, the act of searching shakes us. It reminds us that humanity isn't just looking, a part of us needs it. Because if we're not the only ones, what are we? If we are, what does that say about responsibility, purpose, loneliness? Over the next few minutes, through this part and into the next, we'll explore how these searches work, what they've taught us so far, and why nothing matters more than this question. Because in the night sky, each distant signal is a question echoed across space and time. Are you there? And our answer may define the story of life itself. In 1961, astronomer Frank Drake did something bold. He tried to estimate how many intelligent civilizations might exist in our galaxy right now. He didn't claim to know the answer, but he gave us a way to ask the question better. His tool, a deceptively simple formula, the Drake equation. It looks like math, but really, it's a mirror. Every variable in the equation reflects a deep uncertainty, a vast cosmic mystery. How many stars form each year in the galaxy? What fraction of those stars have planets of those planets? How many are Earth-like? How many of those could support life of those? How many evolve intelligence and of those? How many choose to build technology capable of communication? Finally, how long do such civilizations last? The final number is a product of all of these, multiplying possibility by mystery. And depending on what you plug in, the result ranges from 1 to tens of thousands. And here's the twist. Even if life is common, intelligence might not be. Or intelligence might not last. Maybe most civilizations never survive long enough to reach out. Maybe they destroy themselves. Or maybe they simply go quiet. That last term, how long civilizations send signals, is the most chilling because it's not just about aliens, it's about us. If we expect others to survive and communicate for thousands of years, we must ask, will we? The Drake equation doesn't give an answer. It gives a frame. It tells us where to look, what we don't know, what matters most. And it forces a sobering truth. Maybe the galaxy is alive with signals, but we've only just started listening. Maybe we're early, or maybe we're shouting into a silence no one else escaped. Yet, the silence isn't proof of absence. It's a question, a challenge, a haunting stillness that demands we keep listening. Because one faint signal from one distant world could change everything. There's a question that keeps astronomers awake at night. One simple, piercing question: are we the only ones, not in a poetic sense, but literally, out of the hundreds of billions of stars in our galaxy, each with planets of their own, how many have life, and how many of those worlds might have built cities, radio signals, questions of their own? In the 1960s, scientists started pulling that question apart. They tried to trace a path from stars to planets, to life, to intelligence, not with hard numbers, but with filters, possibilities. How many stars form every year? How many of them have planets? How many of those planets are just the right distance from their stars, where water could flow, clouds could form, chemistry could spark? Then, how often does life actually begin? And when it does, how often does it become something conscious, curious, capable of thought, speech, technology? And finally, once a civilization becomes advanced enough to send out a signal, how long does it last? The truth is, we don't know. Some of these steps might be easy, others could be impossibly rare. Maybe life forms often, but intelligence almost never. Maybe intelligence is common, but technology destroys itself. Or maybe they're all out there right now, but too far, too quiet, or too early, or too late. It's like tuning an old radio, trying to catch a single whisper across a galaxy of silence. And the numbers, they're a mirror. You plug in different answers, and you get wildly different outcomes. One guest says there could be millions of civilizations out there. Another says we might be alone. But here's the thing, even one other civilization would change everything, because it would mean we're not a fluke, that the universe wants life, that we're part of something larger, a cosmic ecosystem, a community we haven't met yet. And if we are alone, then this tiny blue world, this flicker of self-awareness in a cold, dark sea, becomes infinitely precious. Either way, the question matters. It reveals who we are, what we fear, what we hope for, and maybe what's waiting in the silence. So far, we've explored stars, planets, distance, and even silence. But there's a point where questions become too large to sit still, and that's where we are now. Because if the universe is ancient, full of stars, full of planets, and yet completely silent, then maybe the problem isn't out there. Maybe it's us. Maybe it's our assumptions. Maybe the universe isn't what we think it is. Let's start with one of the most mind-bending ideas. What if we're inside a simulation, not a metaphor, a literal, programmed construct? If reality is computational, like a game or a lab experiment, then the reason we don't detect other civilizations might be because they've been edited out, hidden, muted, or never rendered in the first place. Some thinkers argue that if civilizations ever become advanced enough to simulate entire universes, then it's likely that most conscious beings exist inside one of those simulations. And if so, how would we ever know? Here's another: alien civilizations might be invisible by design, not because they're weak, but because they're too strong. Advanced species might operate on scales or in wavelengths we can't detect. They might use quantum networks, gravitational waves, particle fields. They could be here, everywhere, and we'd never know. or they might cloak themselves on purpose. If the dark forest idea is true that shouting into the cosmos is dangerous, then hiding is the only way to survive. The quiet ones might still be out there, watching, waiting. There's also the zoo hypothesis, the idea that Earth is being deliberately avoided, that intelligent civilizations do exist but have chosen not to interfere. We are animals behind glass, a cosmic reserve. Then, there's the most terrifying explanation of all: we're too early. That life, intelligence, even curiosity is only just beginning to bloom. Maybe the universe needed time. Maybe conditions are just now becoming right for consciousness, and we are among the first sparks. If that's true, then we're pioneers, but also custodians. We carry the weight of being the only voice the cosmos may currently have. These explanations might sound like science fiction, but they're not wild guesses. They're models, thought experiments, philosophical weapons forged to pierce the mystery of silence. And they share a strange, common thread. They all shift the focus from what's out there to what are we, really? Maybe the silence isn't empty. Maybe it's structured, designed, glitched, or still waking up. And in the absence of an answer, we're left with a haunting possibility: the universe is either full of life or it's just us. And either way, the implications are staggering. We've talked about stars, galaxies, the visible, the luminous, but most of the universe is missing. Not in the sense that it's gone, but that it's hidden, silent. It doesn't shine, it doesn't glow, it doesn't reflect light or emit heat. And yet, it's there, holding everything in place. We call it dark matter. It's not just a placeholder, it's a necessity. Without it, galaxies would fly apart, their stars would spin off into space like sparks from a grinding wheel. But they don't. They hold together because something unseen surrounds them, a massive, invisible halo. We've mapped it, not directly, but by watching how galaxies rotate, how light bends around clusters, how the cosmos expands. It's always there, a gravitational fingerprint without a foot. What is it? We don't know. It's not made of atoms, not dust, not gas. It doesn't behave like anything we've seen in a lab. It's matter, but it doesn't interact with light. We can't see it. We only see what it does. And there's more. If dark matter holds galaxies together, something even stranger pushes them apart: dark energy. Where dark matter pulls, dark energy expands. It is the force behind the accelerating growth of the universe. The reason distant galaxies are racing away faster and faster. A kind of anti-gravity, not just in space, but of space. Together, these two mysteries, dark matter and dark energy, make up over 95% of the universe. Think about that. Everything you've ever touched, tasted, built, destroyed, loved, the atoms that make up every star, every world, every life are just the final 5%. We are shadows dancing in the light of a deeper unknown. And yet, from that 5%, we've begun to map the 95. With telescopes, math, collisions in underground labs, and simulations run on supercomputers, we shape the outline of the invisible. The universe is not made of what we see. It is made of what holds things together and what tears them apart. And once you realize that, everything changes. You begin to ask different questions. Not just what's out there, but why does anything hold together at all? Why is there something instead of nothing? What's underneath reality? We've spent the last chapters talking about space, distance, expansion, but there's another dimension we've been quietly moving through this whole time. We feel it constantly. We measure it obsessively. But what is it, really? Time feels like a river, always flowing forward. But physics tells us it's more like a dimension. Just like left and right, up and down, we move through time the same way we exist in space. Yet, we can only move one way forward, always forward. But why? Why can't we go backward? Why does time seem to flow? One possible answer: entropy. It's the idea that systems tend to become more disordered over time. A glass shatters but never reassembles. Smoke disperses but never reforms. Entropy increases. It's not just a tendency, it's a law. And that increase in entropy gives us an arrow, a direction, a past, a future. But here's the twist. The laws of physics don't care. they work just as well in reverse. A movie of particles moving backward would still obey all equations. Time itself, in math, has no preference. So, where does the arrow of time come from? It may come from the Big Bang, a universe that began in extreme order and has been unraveling ever since. Time, as we know it, may be the residue of the universe's birth. But time is flexible. Einstein showed us that time is not constant. It stretches, it slows, it bends under gravity. The stronger the gravity, the slower time moves. Near a black hole, seconds stretch into centuries. Time and space are part of the same fabric, space-time. You don't just move through space, you fall through time. And at the speed of light, time stops. A photon, from its perspective, never ages. It's born and absorbed in the same instant. For light, the universe has no duration, only position. Time is not universal, it's personal. Your time depends on your speed, your gravity, your motion. You and I age differently if we move differently. That's not theory. It's been proven with satellites, with clocks, with beams of particles. So what is time? A dimension, a measurement, an illusion, a direction, a mystery. And in all of this, one thought lingers. If time had a beginning, could it also have an end? Could there be places, moments, phenomena where time breaks down, stops, loops? Is the future already written, or still being created, second by second, thought by thought, or are we just passengers, unable to exit the ride? So far, we've mapped galaxies, measured stars, bent space, stretched time, but behind every fact, every number, every question, there's something quietly watching you. Consciousness is the one thing we all know for certain. Not stars, not atoms, not even time. Just this: you are aware. You are not the universe. But somehow, a part of the universe has become you, able to ask about itself. And that is bizarre, because physics doesn't explain awareness. Neurons, yes. Electricity, yes. But the experience of being, of having thoughts, of remembering, of fearing, of loving, that's something else. Let's stop here. Really stop. Right now, you're listening to a voice in your head, a story. But who is listening? Who is the you behind your eyes? This question, what is consciousness, isn't just philosophical, it's a scientific mystery. Because we don't know where it comes from. We don't know how it happens. We don't know why the brain, when structured correctly, stops being a machine and becomes a mind. It might be emergent, like a pattern, or fundamental, like mass. Some even suggest that consciousness is woven into the fabric of the universe, like space and time, that the universe needs consciousness to exist at all. But here's the truly haunting part. If the universe is 13.8 billion years old, and if life only arose on this tiny planet, and if consciousness only emerged recently, then that means for almost all of time, the universe existed in silence. No thought, no awareness, no reflection, just stars collapsing, exploding, without anyone to notice. Until now, until you. Think of that. After billions of years, the universe produced a creature that could look at itself, measure itself, question itself. You're not just in the universe, you are the only known window through which it can see itself. And that makes you rare. Maybe not unique, maybe others are out there, other eyes, other questions, other dreams. But so far, we've seen none. Which means your mind matters more than we ever imagined. Who are you, really? Not your name, not your face, not your story. Strip away the memories, the language, the culture, what's left. Just a flicker of awareness, the silent observer, the thing inside you that knows it's here. That is the self. But where does it begin? And where does it go? In a universe of stars and entropy, black holes and redshifts, the strangest thing might be this: a mind that knows it's temporary, of being aware of its own end. No star knows it's dying, no planet grieves, but you do. You know that time is passing. You know you won't last forever. You feel it. And that knowledge, the awareness of impermanence, is the price of consciousness. It hurts, but it also creates meaning. Death isn't just an end, it's the frame that makes the moment sharp, beautiful, urgent. If we lived forever, Would anything matter? And yet, the mind rebels, we fear it, we fight it. Every story we've ever told, religion, art, science is in some way a reaction to the fact that we are conscious and finite. But here's the strange twist. Everything you've ever been is made of atoms, ancient atoms. The hydrogen in your body was forged in the Big Bang. The carbon in your bones, cooked inside stars. You are made of dead things, and yet somehow, you are alive. And when you die, those atoms go on. They don't vanish, they don't stop, they return to the cycle. From dust to dust, from thought to silence, from silence to stars. So, maybe consciousness is not a thing that's lost. Maybe it's a pattern that arises when the right conditions bloom. A wave, not a particle, a ripple in complexity. If that's true, then death is not a deletion, it's a release. And the universe, vast, dark, expanding, might be capable of producing this flicker again, somewhere else, in someone else, or maybe in some new form beyond anything we can comprehend. But for now, you are the only evidence we have. You are the miracle in the math, the fragile pulse in an indifferent cosmos. And maybe, just maybe, that's enough. No longer floating through stars and distances, but through something more intimate value, the unspoken weight behind every question. Because once you know the universe is vast, and life is rare, and consciousness is temporary, another question begins to burn. Does anything matter? What's the point of kindness, of beauty, of thought in a cosmos that will one day go cold? Why care about joy or grief or art when the stars themselves will die? What is one breath worth when there are trillions of empty worlds where breath has never happened? This is the edge of cosmic depression, a cliff where meaning seems to fall off. The silence of the universe isn't just physical, it's emotional. We cry out for significance, and space echoes nothing back. And yet, we still love, we still dream, we still stare at the sky and gasp, not in fear, but wonder. And maybe that is the answer. Maybe meaning isn't found in the universe, it's brought to it. Maybe we are not here to find purpose, but to invent it, to pour it into the cracks, to build it fiercely, like a fire in the dark. The fact that the universe doesn't assign you a reason is your superpower. Because that means you choose. You choose what matters. You choose who you are. You are not here to be measured. You are here to mean. And look what we've done with that freedom. We've written symphonies, fallen in love, painted the stars. We've sent robots to other planets, cured diseases, held dying hands, cried at poems. We've taken the chaos of physics and turned it into compassion. No other creature, as far as we know, does that. So, if meaning is rare, so what? So is gold. So is light in deep space. So are you. The universe doesn't owe us purpose, but somehow, we give it one anyway. And that changes everything. You build something, you speak a truth, you love someone, and you wonder, will it last? That question hides inside every act of creation. Every sculpture, story, or whisper in the dark is a quiet rebellion against time. Because deep down, we know everything fades. Empires fall, stars burn out, even memory slips. The universe is ruled by entropy, the great unbuilder. It ensures that over time, energy spreads, structure dissolves, heat evens out. It's why ice melts, why fire dies, why no machine runs forever. And one day, it's why the universe itself may grow cold and dark. But still, we build the pyramids, Voyager's golden record, songs passed from voice to voice, digital libraries encoded in crystals, a message written in binary drifting out of the solar system toward no one. Why? Because even if we can't stop time, we can leave fingerprints in it, not permanent ones, but long enough to echo, to ripple forward, to remind some future intelligence, or maybe just the void, that we were here, we thought, we dreamed, we reached. There's a strange nobility in that. Consider Voyager 1, launched in 1977, now over 14 billion miles from Earth. It carries images, greetings, music, a time capsule in the dark. It will drift between stars for billions of years, long after Earth is gone, long after the sun is cold. And maybe nothing will ever find it. But that doesn't matter. What matters is that we sent it, that we said, we existed, we tried. So, what survives? Not the buildings, not even the species. Maybe the story, maybe the act of caring, maybe the choice to create beauty despite knowing it might not last. And if all that disappears, if entropy swallows every word, every memory, every piece of art and architecture, then perhaps what matters is that it happened at all. You lived, you thought, you burned with consciousness in a universe that didn't ask you to. And that is something. For centuries, we've looked up and wondered, is anyone out there looking back? Not just stars, not just planets, but minds, questions, stories, a gaze returning our own. It's the most ancient hope of all spacefaring creatures that we are not alone. But what would it mean to actually make contact? Not with microbes or fossils, but with a civilization, with a species that knows it exists, that has built tools, language, maybe even stories. Maybe they've stared into their own night sky and asked the same question. We often imagine first contact like a scene from fiction ships, greetings, translation, but the truth would be stranger. Because if we ever did hear from an alien intelligence, it would likely be a signal, a pulse, a burst of data sent long ago across vast light years. It could arrive as radio waves, a laser, a burst of neutrinos. By the time it reached us, the senders might already be gone. Still, we'd decode it, analyze it, obsess over it, because even a fragment, a word, a number, a pattern would be everything. It would prove we are not a fluke, not a cosmic accident. It would connect us to something larger, older, parallel, and yet, there's something sobering in that dream. If they're more advanced, the gap between us might be insurmountable. We might be like ants receiving a broadcast from a cathedral. We might not even recognize it as language or meaning. And if they're less advanced, if we find ruins or echoes or dead signals, we become the elder voice, the keeper of memory. In either case, contact would change everything. Our religions, our science, our understanding of life, purpose, time. We'd stop thinking only about Earth. We'd begin to see ourselves not as nations or tribes, but as a species, a single voice echoing across the stars. Even the attempt matters. SETI, MITI, golden records, deep space beacons. They're not just about finding aliens, they're about defining ourselves. What do you say to someone you have never met? What do you send to the stars? Music we wondered, we reached. What if no one answers? What if we send messages, launch telescopes, scan skies for centuries, and hear nothing but the quiet hum of physics? No contact, no signal, no ruins, just silence. It's easy to feel disheartened by that, to imagine an empty cosmos, cold and indifferent, to believe that we are alone, stranded on a pale blue island surrounded by an ocean of stars that will never speak. But maybe we've been looking at it the wrong way. Maybe the silence isn't rejection, maybe it's an invitation. If we are truly the first, or the only, species to awaken, then we are the voice the galaxy has been waiting for, the story that's just beginning, the torchbearers in a universe not yet filled with song. That means this moment, our moment, carries unimaginable weight, because what we do next matters. Will we turn inward, divide, destroy ourselves before we leave the cradle? Or will we reach outward, build, explore, learn, survive long enough to become the ones who send messages to future minds? Imagine this 1,000,000 years from now, a young species, just learning to listen, hears a signal, ancient, simple, unmistakable, you are not alone, we were here, and we made it. That signal could come from us. We could be the first page in the book of galactic civilization. We could be the myth, the memory, the voice that survives. And if that possibility exists, even faintly, then our job is clear. We must earn our place in the story, not just through technology, but through wisdom, through kindness, through art and music and science, through everything that makes consciousness beautiful. Because if we are the first, we set the tone. The cosmos doesn't give us purpose, but it gives us time and space and silence. What we do with that silence, that's on us. We often think of the future as tomorrow or next year, maybe a century ahead. But what about 1 billion years from now? What does the universe look like? Not for us, but for time itself. Let's begin with stars. Our sun has about 5 billion years left. When it dies, it will swell into a red giant, then collapse into a white dwarf, a hot ember slowly fading in the dark. Other stars will do the same. The massive ones will explode into supernovae, leaving behind neutron stars or black holes. The smaller ones will quietly flicker out over trillions of years. The night sky will dim. Galaxies will change, too. They'll collide, merge, settle into massive elliptical structures. The Milky Way and Andromeda will become one, a giant, silent swirl of aging stars. Eventually, star formation will stop. The raw material, gas and dust, will run out, and new stars will no longer be born. That's when the universe enters the degenerate era. Black dwarfs, neutron stars, rogue planets drifting between dead suns. A cold, sparse graveyard of what once was. But it doesn't end there. Over unfathomable time spans, even those remnants will vanish. Black holes will evaporate through Hawking radiation, their mass slowly leaking away over quadrillions of years, until not even gravity remains. And then, only darkness, no stars, no light, no energy, just a thin, cold fog of particles stretched across an ever-expanding void. This is the heat death, the universe's final whisper. No chaos, no fire, just stillness, maximum entropy, a perfect, silent equilibrium. It's hard to imagine, harder still to accept. A place where even memory fades, where time itself continues, but nothing happens. And yet, here we are, on a small planet in the early universe, thinking about its end. That is miraculous, because even if the future is dark, we are the light now. We are the meaning, the motion, the music. And maybe that's the point, to burn brightly, not forever, but fiercely. To be conscious while the universe is still young enough to care. We are not the finale. We are the opening act. So, we've traveled to the edge of the cosmos. We've watched stars die, galaxies fade, and time stretch into stillness. And now, we return to this moment, to you, sitting here, breathing, listening, alive. The universe doesn't care what you do. It won't punish you. It won't reward you. It won't applaud your dreams or mourn your mistakes. But you care, and that changes everything. Because if all of this stars, atoms, consciousness, language is truly temporary, then you are the rarest thing of all, a creature aware of its own impermanence. And here's the truth. The size of the universe doesn't diminish you. It dignifies you. The fact that you are small is what makes your choices powerful. The fact that your time is brief is what makes your time precious. Every act of kindness you offer, every truth you tell, every life you touch, every piece of art you create is done in defiance of cosmic silence. It's a flare, a fingerprint, a ripple of intention across an ocean of indifference. And maybe that's what makes us special. Not that we understand the universe, but that we care about it. We give names to stars. We build telescopes just to watch light from a galaxy 13 billion years away. We fall in love under the sky. We send poems into space. We wonder. We've walked through stars, drifted beyond galaxies, stood at the edge of time. But now, we're back on Earth. The air is warm. Your chest rises. Your heart beats once, then again. And suddenly, the question becomes not how the universe works, but what you choose to do with the tiny slice of it that you've been given. Because here's the truth. We live in a universe that's old beyond comprehension, expanding, cooling, slouching towards stillness. But in this fleeting moment, you are alive. You are matter that can feel, a pattern that knows it's a pattern. The stars built you, yes, but you can now look back at them and whisper something they never could. I understand. So, what do we do with that? Do we build, destroy, dream? Do we turn inward, obsessed with smallness and survival? Or do we reach toward knowledge, toward empathy, toward each other? The universe doesn't care. It has no preference. But maybe we should. Maybe the meaning of life isn't written in the stars, but in what we choose to protect, what we choose to imagine. Maybe the purpose of a conscious species isn't to live forever, but to make something worth remembering before it's gone. Because if we really are alone, if no one is watching, if no signal ever comes, then everything we do matters more, not less. Every act of kindness, every discovery, every poem, every shared moment under the night sky. They are not small things, they are everything. They are the only parts of the universe that know they exist. So, maybe, in the end, the question isn't how big is the universe. Maybe it's how big is your response to it. You have this one lifetime, this one mind, this one chance to be a spark in the dark, and you're not alone. We're here, too, thinking, asking, reaching with you. Let's go back to that ridiculous, brilliant line. You may think it's a long way down the road to the chemists, but that's just peanuts to space. At first, it was funny, a cosmic joke. Now, it feels like an understatement, because after tracing the edges of time and light, walking the structure of galaxies, bending through black holes, and spiraling into consciousness, one truth becomes impossible to ignore. You are tiny, but that's not an insult, it's a revelation. You are not insignificant despite your size, you are significant because of it, because in this vast, uncaring expanse, you care, you search, you wonder, you ask questions no other creature, no star, no atom has ever asked. And somewhere in all of that, the scale flips. The road to the chemists becomes beautiful, the ordinary becomes sacred. The morning sun on your skin isn't just weather, it's a star 150 million kilometers away, flooding your cells with energy forged in a nuclear heart. The water in your glass is ancient hydrogen born in the Big Bang. The iron in your blood is supernova dust. Your breath is recycled stardust. Everything is vast, but you are aware of it, and that makes all the difference. We zoom out, not to lose ourselves, but to find out where we really belong. Not at the center, not above, not below, but within. The universe isn't a thing we live inside. It's a thing we are a part of, and a part of us. So the next time you walk down the street, look up, not for answers, but for context. You're not just moving through a city or a planet, you're moving through a living miracle, a brief flare of thought in a universe mostly silent. But maybe, just maybe, it's listening now. Everything we've explored, stars, atoms, galaxies, time, life, it all leads here, to the edge of wonder, not the edge of knowledge, because knowledge has edges, but wonder doesn't. By now, you know the facts. The universe is 13.8 billion years old. It's expanding. It's massive. It's cold. It's dark. You are made of stardust. You are temporary. You are miraculous. But facts are not the end. They are the doorway. Because after all the data, all the theories, all the stunning realizations, something remains. A silence that no formula explains. A weight behind the stars. A feeling that something is still missing. Not because the universe owes us meaning, but because we keep asking for it anyway. And maybe that's the last great paradox. We are creatures who evolved to survive, to eat, to run, to reproduce. And yet, here we are, talking about infinity, grieving stars, crying at galaxies, longing for connection with things we've never seen. We were born for breath and heartbeat, and yet we ache for eternity. And that aching, that reaching beyond what's necessary, what's explainable, that might be the most extraordinary thing the universe has ever done. It made something that asks. And here's the final twist. Every time we get close to answering the big question, how big is the universe? A bigger one takes its place, and what came before it? Why is there something instead of nothing? What is beyond space and time? Where does the edge end? No one knows. Maybe no one ever will. And maybe that's perfect, because mystery is what pulls us forward, not just the size of the universe, but the size of the questions it leaves behind. You are not lost in the cosmos, you are lit by it, briefly, brightly, now. And maybe that's the one thing the cold, expanding void can never produce on its own wonder. So, what now? Live, create, connect, tell stories, build bridges, ask questions no one else dares to ask. Be kind, not because the universe demands it, but because you choose to be. And when you look up at the stars tonight, don't feel small, feel rare, feel temporary, feel awake. This is your moment. This is your chapter in the cosmic book, and no one else gets to write it but you. Let's stop counting. No more distances, no more timelines, no more parts, just this. You, here, now. After 30 chapters of stars and silence, of equations and awe. The mind is full, but something deeper stirs. Not thinking, not understanding, just a kind of stillness, a soft hum in your chest. Because you've felt it by now, haven't you? The truth hiding beneath every number. This wasn't a documentary. It was a mirror. And through it, you've seen something larger than the universe. You've seen yourself. You are small, but not meaningless. You are temporary, but not irrelevant. You are a flicker of consciousness. So brief, so delicate, but carrying questions that could echo into the bones of the cosmos. In a universe where galaxies live and die without ever being noticed, you noticed. That alone is extraordinary. So, here at the edge, we leave you with no answers, just a feeling, a tension between fear and wonder, a silence you can't quite explain, a tear you didn't expect, and maybe a smile, because the point of this story was never to explain the universe. It was to remind you that you're a part of it, a rare, fragile voice inside a vast, unfeeling song. And still, you sing. So, if the universe feels stranger now, or maybe a little more beautiful, consider engaging with this exploration further. There's always more waiting. There's a border you've never touched, but it defines everything you know. It's called the cosmic horizon, the edge of the observable universe. Not a wall, not a place you can travel to, but a limit, a boundary drawn by light, by time, by the speed of causality itself. It's the farthest distance from which light has had time to reach us since the beginning of the universe. Roughly 46 billion light years in every direction. That number sounds final, concrete, but it's not. Because beyond that edge, beyond the visible, is something we can't yet see, can't yet measure, but know almost certainly exists. More galaxies, more matter, more space, possibly more versions of reality altogether. That's the hardest part to comprehend, that what we've seen, everything we've mapped, photographed, simulated, touched with radio waves and telescopes, is not the whole. It's barely the beginning. A grain of sand in a beach of unknown size, a drop of dew on the edge of a cosmic storm, and what lies beyond, no one knows. It could be more of the same. An infinite stretch of stars and voids, clusters and filaments, repeating forever. Or it could be stranger, regions with different laws of physics, different particles, different versions of causality. It could be curved back on itself, folded, stitched together with dimensions we can't perceive. Or it might end abruptly, unimaginably. But here's the deeper truth. The edge we speak of is not just physical, it's philosophical. Because the observable universe isn't just the edge of what we can see, it's the edge of what we can know. And standing at that edge, we are left with a question that haunts all thinking beings. Is this it? Is what we know all there is, or is there something beyond, unreachable, unknowable, yet still real? It's the kind of question that doesn't just challenge science, it challenges humility, because we must learn to live with not knowing, to breathe in mystery, to make peace with limits. But in that surrender, something beautiful happens. We become explorers again, not of lands or planets, but of questions, of meaning, of curiosity itself. And maybe that's where our greatest purpose lies, not in answers, but in the act of reaching, in wondering, in not being satisfied. We stand at the edge of the visible universe, not with maps, but with imagination. And that's enough for now. There is a question we've avoided, not because it's forbidden, but because no amount of data can answer it. It's not about galaxies or atoms, not about distance or time. It's about what lies beyond knowing. We've traveled billions of light years through this story. We've collapsed stars in our minds, stretched the fabric of space, traced the breath of consciousness, and faced the end of time. But eventually, every map ends in a blank space, marked not with coordinates, but with silence. And in that silence, something lingers, a final paradox. Because the more we learn, the more we zoom out, measure, discover, and understand, the more we realize how little we truly know. The horizon moves, but we never catch it. Every answer births a deeper question, Every breakthrough reveals a wider darkness. So, what is this feeling, this ache behind your ribs? This stillness that's not quite peace? This flutter at the edge of comprehension? It is wonder, but it's also fear. Because if the universe is infinite, then so is your insignificance. But if it's finite, so is your meaning. If we are alone, then we are unbearably precious. If we are not, then we are just one voice in a vast choir we cannot hear. Either way, the truth is unbearable and beautiful, and it won't stop echoing. What made the universe? Why does it exist at all? What is the origin of the laws that govern everything we've seen? Is there something beyond this? Something outside of existence? We don't know. We may never know, but we keep asking. And maybe that's the point, because in a universe filled with blind forces and indifferent stars, here you are, asking impossible questions, dreaming, grieving, building meaning from a dust cloud lit by fusion. You don't just exist, you wonder why you exist. And that's the most powerful force in the universe. You are not a conclusion, you are a continuation, a story that refuses to end, even when the last page is unreadable, a flicker that will burn and question and reach, no matter how dark the night becomes. So, here at the final edge, we leave you not with a period, but with a pause, because the greatest question the universe gives us is the one it never answers. And maybe that's the most human thing of all, to stand at the edge of forever and ask, one more time, what else is out there? The screen fades to black. No more visuals, no more numbers, just the sound of your own breathing, and the universe still out there, humming beyond your comprehension. You've come a long way, not in space, not really, but in something deeper. You've expanded the boundaries of your mind, stretched your imagination to the edge of time, faced mortality, mystery, the unbearable size of everything, and somehow you're still here. Not broken, not lost, but wider. That's what wonder does. It doesn't answer the question, it deepens it. It doesn't bring peace, it opens you. The greatest gift of the universe isn't knowledge, it's perspective. You are here for a blink. And yet somehow, that blink holds entire galaxies. You are made of fragile flesh and neurons. And yet you contain stories the stars cannot tell. The universe is not yours to conquer, but it is yours to witness, to marvel at, to carry in your chest like a secret fire, and maybe, if you're lucky, to pass it on. Because wonder is contagious, it echoes. Questions live longer than answers. So, share this feeling. Tell someone, not the facts, not just the billions of light years or dark matter or entropy. Tell them what it felt like to be small, to be aware, to be a question walking through the dark. And if anything in these past 2 hours moved you, if a thought haunted you, if a line lingered in your chest, if your idea of reality cracked open just a little, then engage with this journey. There is so much more waiting. But for now, we rest. You are not in the universe. You are not separate from it. You are the universe asking itself what it means to be. And that question is still unfolding.